So um, the recording will be available on the website. The website for this workshop, I will post it here on the chat window. In the website, you will have access to all the slides, all of the material that you would need to complete this, the hands-on activities as well as the slides. So this workshop is organized by the University of South Carolina with EPIC, the Engagement and Performance Operations Center, and also the MSCC, the Minority Serving Cyber Infrastructure Consortium. It's going to be a two-day workshop. The first day will be focusing on topics related to BGP, first understanding the fundamentals of BGP, then providing some hands-on exercises. So we will see how we can apply those topics described in the set of slides. And then after the second break, we're going to look into what Science DMZ is, some fundamentals of Science DMZ, as well as some demos that would show the impact on the performance that Science DMZ can bring to your network. So I have here also George and Jennifer. So George, if you would like to unmute and introduce yourself.
Yeah, hi, thanks for having us. I'm George Robb with EPIC. I'm out of Energy Sciences Network. I'm a member of the EPIC team, and I get to attend workshops and help teach and perform or make science perform better. Glad to be here, and thanks for having me.
Thank you, George. Thank you for joining. And also we have Jennifer Kim from MSCC. Jennifer, are you there?
I am. Hello. Hi, everyone. I'm Jennifer Kim, a cyber infrastructure engineer with MSCC, which is in partnership with Internet2. In my role, I work with institutions to further their cyber infrastructure goals. So I work with a variety of different persons on the campus.
Thank you, Jennifer. All right, so I think now we can get started. So I'll hand it over to George to start with the BGP fundamentals.
Excellent, thanks. Let me share screen, and hopefully we'll have a fun review for several and/or an exciting adventure into BGP fundamentals here. Help me keep check on time too. I do not wish to go over or take in out of the lab in any way, shape, or form. So BGP fundamentals. Once again, I'm George Robb. I've been playing with computer networks, HPC, and compute as a professional for about 27 years now. I've got a passion for tuning hardware, and I'm always chasing performance. Energy Sciences Network, as I mentioned, our map is behind my head. It's ESNet. It's my day job. I'm part of the data and facilities team. So we're enterprise platforms, network, compute, and storage for all of Energy Sciences Network. And then I get to have a lot of fun with EPIC, or the Engagement Performance Operations Center team. I joke around, I get to play Batman from my day job. The Engagement Performance Operations Center, or EPIC, we are a group that make science go through active engagement, through assistance with scientific workflow and analysis, and then workshops like this. Again, thanks for having us. We love doing these workshops. We love being able to help teach and inform. Anytime you have questions, reach out to us. We're here to help. So, to the topic at hand today, Border Gateway Protocol. What is it? Let me start with a little bit of history. Back in 1989, Kirk Lockheed and Yakov Richter were at lunch, and they said, hey, we need to come up with a workaround for how the internet behaves, functions, and works. This is the literal 3 napkins. If not mistaken, I believe they are framed at Cisco headquarters, and it's been in use since 1994. The Border Gateway Protocol is the routing protocol used by network engineers to exchange routing and reachability information between autonomous systems. So ASNs, AS numbers, groups, which are typically large networks operated by the internet service providers or large institutions and organizations. Example being, ESNet itself has 2 ASNs that we use on a daily basis. I'm sure your organization probably has an ASN, and it's where peering happens. A little diagram below, BGP makes 2 ASNs able to talk to each other. BGP is a path vector protocol, meaning that it's used for vector of AS numbers to determine the best path for forwarding packets. BGP routing decisions take into account factors such as AS paths, origin types, and policy rules configured by network administrators. So remember path vectors, magnitude and direction. There's a cost to be able to hit a specific path. BGP is also a highly scalable and robust protocol that is designed to handle large networks with multiple connections to other autonomous systems. It provides a high degree of control over traffic flow and can be used to implement complex routing policies and traffic engineering strategies. Again, I show a map of a larger network, our ESNet 6 map. A lot of traffic engineering goes into play here, and BGP is the glue that sticks it together. So configuring and managing BGP can be challenging due to its complexity and potential for misconfigurations, i.e. large-scale outages or disruptions. One of the most famous ones is the February 2008 YouTube outage, where a country introduced routes that caused YouTube to flat out fail and their routers to melt. The source, I believe it was the country Pakistan that did the source, and the Pakistan routers melted. All this being said, BGP makes the internet, quite literally, and in most cases, it just works. Let's have a few words about routing. So, research and education routing versus commodity routing. Research and education routing, or research and education networks, are typically built around bandwidth considerations, built around performance considerations, and also built around stability with deterministic open architectures. You can talk to your regional, you can talk to your upstream provider, you can talk to your network engineers in an R&E network. They're very open and able to work with you to make sure that your paths are optimized. Community, they're also built around community, they're built around educational needs and research. R&E networks are primarily designed and engineered to support science and education. Commodity routing or commodity networks, carriers, general purpose ISPs, so on and so forth. They're engineered for things like DDoS protection, uptime, private business needs, private business architectures, commercial, traditional, for-profit traffic. There's factors like traffic shaping, traffic policing, inspections, methods for ad revenue and injection, bandwidth restrictions, data caps, so on and so forth. You can see where science wouldn't get along too well with a nice ad for something as you're trying to get an elephant flow across the continent. Research and education networks are engineered to support science and education foremost. Commodity networks, in a word, are not. We wish to keep and engineer our scientific traffic on the science networks. So let's get into a few pictures about routing with BGP. Example, regional R&E networks in the United States. So this is provided by the Quilt. As you can see, there's just a few. These are all tied together via BGP. I'm sure you all see your network represented on here somewhere, and if not, let's get it there. So a few more discussion points about R&E versus commodity. So what's the difference, right? So let's start out in the Googles, GCP, AWSs, things of that nature. There's multiple cloud providers, Amazon, Google. AS numbers of them are well-known, well-established, and they're the cloudies. Then you have those that connect up to your ISPs, example being your home internet provider, regular community regional ISP. And then you'll have companies that connect up to business class ISPs that then have a path into Google and Amazon and other business paths. So there's many ISPs, many cloud providers, and many companies. In the red circle is where we start getting into the scientific and research and education platforms. So example being Internet 2, Science Network Connectivity for state and regional science networks. Energy Sciences Network, we're big science facilities, DO labs, Office of Science Research. National labs and Office of Science facilities are here. Again, you see the mesh starting to be a border. And then I'll even have on the internet too, the science networks and regional science networks. I'll go back a slide to these so you can think about the R&E pathing. Then we have traditional regional networks such as university schools and libraries. You'll notice that they have paths out through their regular ISPs. The Zaos, the sockets, the Lumens, AT&Ts of the world, where there will be a path out that direction. And then there's also a path into the R&E direction. So this would be at a regional network's border. Then you have international, such as GIANT or European RINs. That's where the TEs or some of the traffic engineering and the TAs, the transatlantic links, come in. Once again, to the maps, we have a lot of cross links. So we'll go over to CERN, GIANT, and a few other peering locations. So this brings all this in, and then R&E can happily work together. Again, there are more than just, there are many is the best way to say it. And again, I'll highlight the many. How to support R&E with BGP and routing. We use BGP policies to keep R&E traffic on an R&E network and to keep it performant and tuned. Keep in mind in the background, BGP announcements will attract traffic. Routing determines the path the traffic takes in the network. BGP basically gives us the tools to route. Again, BGP is a path vector protocol, so for a given prefix, the shorter AS path is preferred. If an AS path length is the same, then other criteria are used in order to leverage BGP path selection through algorithms. Stay tuned on that. We have a talk literally towards the steering and towards the path selections in a little while. So how do we continue to support? Network engineering at a few points. We'll want to tune or optimize via overriding BGP's use of AS path links when choosing between R&E and commodity, for example. R&E paths tend to be potentially longer in the general case, and there's even longer once the more organizations are involved. Using normal BGP route selection between R&E routes and between commodity routes, we'll want to tune those. Hop count, that is a legacy metric. Avoid using it. Again, we'll cover that a lot more later. And here's an example of, again, another photo or another diagram that gets a point, this idea. So we have these AS numbers, and we have these various paths. So let's say our science DMZ is trying to get from this DTN all the way over to this DTN. Multiple paths, multiple regions, multiple campuses. As we can see, the AS path link through commodity and 10 gig and 10 gig, which also may cost per ingress and egress, is short. For traffic engineering and for BGP tuning, we'll actually want to take the longer path, and here's why. We have 100 gig through regional 1, 100 gig through regional 2, 100 gig through regional 3, and 100 gig into campus 2. This path is more performant and more optimized. And as time moves on, this is actually an older slide, you'll notice these hundreds turning to 2s and 4s and 800s, whereas the commodity providers are still worried about connectivity in the 10s and the 100s, again, with the dollar figures and the commodity. All that said, stay tuned for the next part about BGP. We'll have a talk here in a little while about local preferences and MED at 14:30 Eastern. So again, thanks for having me. And I think we may have just a few moments if there's a question or two.
Thank you, George, for this great introduction. Yes, we have a few minutes for questions. If there's any question, please feel free to unmute yourself, or if you prefer, you can type in the chat window. And the slides are already on the website. So If you want to go over them, you can simply just go there and download them. All the slides that we're going to discuss in the workshop will be available on the website as well. All right. I don't see any question. So again, thank you, George. Now we can move to the next session. So the next session is a hands-on lab. This is gonna be conducted by Jose Gomez. Jose is an assistant professor at the Fort Lewis College, and he will be running this session. So Jose, feel free to share your screen and get started. Oh,
There's a
1
question.
second.
We have a question.
Yes. George, you want to take that?
Yes, certainly. Okay, so where is the BGP attribute concept coming to play? So from this description, BGP is best described as how one internet service provider or one regional is able to talk to another internet service provider or another regional. Or taking it even a step further, there's a concept known as internal BGP and external BGP, where your routers, so this would be in your core of your network, your routers can talk BGP to each other and BGP out to the ISPs. We'll cover this a lot more detail in the steering mechanisms, but the takeaway out of BGP is it is a concept for how routers talk to each other and share routes and paths. It's how the internet works. Route A, route B, path A, path B. If that answers the question. Thanks for asking. Great question.
Great. All right, Jose, you can get started. And if you still have questions, feel free to push them there. Oh, there's another question.
Oh, excellent. So the question is, hi, any new important attribute in MP BGP compatibly only with BGP? MP BGP. Let me take a few seconds to see what MP BGP. I'm not sure what the MP BGP is standing for there. Multi-protocol BGP, extension border gateway protocol that allows for exchange of routing information for multiple layer protocols, not just IPv4 unicast. It enables BGP to handle various families like IPv4 and IPv6 within. Okay, that is excellent. This would be something that I would want to talk to our core routing team. I'm on the data and facilities team where this is interesting. I know that there is a federal mandate to get all federal systems IPv6 only by 2025. That is quite the effort. The MP BGP is a great concept, and knowing that it supports multiple protocols will be incredibly useful. I know that when you're peering two routers to each other, it's traditionally been via the AS number and v4 only. v6 has been in use for a very long time, and the MG or MP BGP will become more and more important as time goes along. So again, that's great. There was one more. How about if you're using OSPF, how will it interact with internal BGP? Again, a great question. OSPF and routing protocols. ESNet tends to use ISIS. OSPF can be zoned to how you want your regions. How will it interact with internal? Oh, yes, excellent. It can be done through route redistribution, but perfect answer. So thank you.
Yeah, we have a lab on that, like in the hands-on session. We're not gonna be doing it today, but like if you're interested, we have like a lab where we run OSPF and BGP, and we show how you can inject routes from OSPF to BGP. But if that's what you're asking about, but if basically could be like another way to interpret the question is that if you're asking about like the administrative distance, then OSPF has a higher priority than BGP if you're talking only internally.
Oh, I love the security questions. There are always security concerns and security questions. The early BGP implementations were truly friends talking to each other and saying, or ISPs talking to each other and saying, hey, let's peer. And that was that. That was it. That you established a session, you configured your side, you configured their side, and you're up. Yes, BGP hijacking is a thing. There are a lot of security considerations. There's a lot of parts. Matter of fact, in the talk a little later, I won't go too much. There's a concept known as ACLs, access control lists. I consider them a steering mechanism in BGP. Blocking is a valid steering mechanism.
Yeah, and just to add a little bit to the few questions that were asked, I believe, and Ali, correct me if I'm wrong, but we have a lab on MP BGP, right? And the BGP security ones as well.
Correct. Oh yeah, I just posted that. I can post the link of the website. So we have a few labs on BGP security. One of them is hijacking. Also, as
So
George was saying, like you can just advertise whatever and the peer will basically accept it. So if you don't have like authentication or if you don't verify who's you're getting your routes advertisement from, you can definitely be kind of hijacked or spoofed. And there are a lot of ways for mitigations. Like one commonly used and recommended approach is RPK, reverse path forwarding. Well, I can post more in the link.
yes, and here I have shared on my screen the labs available within this library. So now Jose will go over one of those labs. However, because due to the time constraints, we're not going to be able to do all of them. But you already have access to those labs. So if you want to learn, for example, ASPath BGP attribute, there's a lab on that. Route reflection, next hop attribute, and so on. So all of these are available and you can run them. For the next session, the one that Jose is leading, this is gonna be the first hands-on session, essentials of BGP, eBGP, and iBGP. All right, so these were great questions. Keep them coming. Meanwhile, Jose, I will stop sharing and feel free to get started.
Thank you, Lee. So let me share my screen. Hopefully you can see this one. Well, let me introduce myself.
Yes.
My name is Jose Gomez. I am an assistant professor at Fort Lewis College, and I will be leading this session. The goal of this session is to get familiar with the platform, which is NetLab, the one that we use to run the labs. We are going to go over the login process, and in the lab activity, we are going to do the basics of BGP. We are going to use Mininet, the tool that we use to generate traffic, and run the BGP tools that we use to configure the BGP routers. And we are going to establish, we are going to use iBGP in order to establish a relationship between two BGP routers. So that's basically the activity. And let me start with the list of labs that we have here. This is the lab series that we prepared. Each lab contains a lab manual that goes over the steps. The first two labs introduces the tool that we use, which is Mininet, and the second one introduces the routing tool that is the free range routing that we are going to use in this lab. The lab that we're going to run today is Introduction to BGP, and also Ali will be running a more advanced lab, which is hot potato routing and BGP local preferences. But in the middle, you can see that we cover, for example, BGP authentication. We're covering about where we can establish some security credentials in order to peer to BGP neighbors. So that's explained in Lab 5, for example. And we have many other topics where you were discussing here. We have the one that redistributes the OSPF routes. I think that's Lab 8.1. The steps are there, and you will have access to this lab series for at least 6 months. And you should be able to extend this as well upon request. All right, so let me talk about the organization of the labs. Each lab starts with a section overview. We have the objectives, topology, the lab settings. Anytime you will need a password, that password is provided in the lab manual. And in section 1, we provide some background information. We explain the topic that will be covered in the step-by-step section, which is in section number 2. Let's talk about the lab activity that is covered in lab number 3, which is Introduction to BGP. But before that, some logistics here. This session is posted here. All the materials related to this session is posted on this link that I think we already shared in the chat window. And also you have the link in the email that you received for the registration. You have the email that contains the credentials. I think Samia, thank you, Samia, is sharing the credentials now. So what we will do, we're going to take our time and we are going to make sure that you have access to a NetLab. And I will show you how to schedule a reservation so we can run lab number 3. All right. So what we are going to do in this lab is basically we have router R1, router R2. We are going to configure BGP in both routers. We are going to establish a relationship so router R1 can share the attached route, which is simply this network that we have here. Let's call it network 1. So network 1 should be reachable from network 2. So, and vice versa. That's basically the goal of this lab, and we're gonna do that using BGP. Here we have the commands that are similar to the ones that you see in Cisco IOS. We're gonna establish a relationship between 2 BGP routers, and we are gonna also advertise the networks attached to these routers. We're gonna verify the information. We're gonna show the routing table as the one that you're seeing here. And also we're gonna check the BGP table and also the BGP neighbor relationship table. This is the BGP table, and as a result, we should be able to have converge information on the reachability of the 2 networks that are remote for router R1 and router R2. All right, let's access the platform. What I will ask you to do, and I will do this with you, is to click on this link and use your credentials to access it. The password is NSF-2025. After the first attempt, you will be required to set a new password, and that will be it. If you have issues, for example, if you have already logged in and you forgot your password, feel free to write it down on the chat and Samia will handle it and will reset your password. So,
Jose, let me just pause you for 1 minute. There's a question if you want to address that in the chat.
Yes, let me check. Here we have a question. What kind of routers are we using? In this case, we are using a software router that is called a free range routing. That one implements the routing protocols that are commonly used, like static routes, OSPF, BGP, ISIS, and many other protocols. This is a software router, and I think George is sharing there the link. Let me open it. This is the project. This is a free open source internet public routing suite implemented in Linux, and we have it for implementing like any routing protocols. And another thing that I don't know if we posted that one, we let me just mention that later, but we can share also the virtual machine that we use for the test here. So in case you wanna run something that is customized on your own facilities, we have the resources to share so you can deploy it on your own. So let's log in into NetLab. Let me try my test user that I will use for this session, and will be test user 1, and the password I think is NSF-2025 altogether in lowercase. After login, if everything goes well, you will be required to set a new password. Let me do that very fast. After that, you might want to provide your email address. I will just provide mine. And you have to set the time zone, I think. I will just set it to Mountain Time, the format, and that's it. After that, your new account is ready to use. Again, let me remind you, in case you forgot your password or anything, you can email me or email Samia, who is in charge of this platform, and we will be restoring your credentials. All right. Before we schedule a reservation, let us know if you have any issues at this point, so we can troubleshoot, so you can do the lab with us. All clear. Thank you, Luis. Good to know. So great. Now, what I will do is show you how to schedule a reservation. You just click on this blue button, new lab reservation, then select schedule lab for myself, and that will directly take you to the BGP lab series. Here you can see that we have the labs, and we have also some exercises in case you want to test your knowledge. We have all here. And today, or in this session, what we're going to be doing is lab number 3. So what I will do is I will click on lab number 3, Introduction to BGP. In that way, I will have access to the pods. And I can see that many of you already scheduled a reservation. Great, great. But if you are new here, what you have to do is, well, you can see that we have the calendar application, so you can schedule a reservation ahead of time. But that's not usually the case because we have plenty of resources. Let me show you. You see this right arrow here? You just click on that and you go to the right, and you can see that we have many pods. Each column in this view represents a pod, and you can use any of these to run the labs. There's no restriction on them. So let me just go way to the right and select, for example, this pod. And let's say that you want to schedule a reservation right away. Well, you just click on the red line here. That means that I want to have the pod available now. We'll click on that, and this will be the view. So let me schedule the lab for like an hour. So here you can see your information. I am a test user. And here you can see the start time, which is now, and the end time. Let's set it for like an hour. So I will schedule this reservation for around an hour. So once you're there, click on submit. And what is happening in the background is we are initiating a virtual machine that is running on a hypervisor in order to provide us with the environment to test these labs. And after you click OK, this will be the view. You see your reservation here. Your reservation is active. You just click on Enter Lab. And what you will see is simply the client machine. This is just a VM. You can click here on this icon, or you can use the tab here to switch to the client. We'll click it here, and you will see that we have a virtual machine. This is a Ubuntu Linux, a lightweight version of Ubuntu that contains everything we need for this activity. And also, because this is a virtual machine, we are also sharing this with you You can download it and deploy it on your local PC. It's very lightweight, so you shouldn't have major problems with that. And the reason why if you want to do custom things, I recommend you to run it on your PC because this environment is not persistent, meaning that whenever you are done or whatever change you do in this VM, you create a file, you do some changes, change some variables, parameters. In this Linux operating system, you will be, everything will be removed after your reservation ends. The reason why we implemented it in this way is just to have a consistent environment to test the point of the labs. All right, I see a question here. Not really technical, but I was wondering if the platform at NetLab is open for public or external use. I am currently teaching networking and would love to explore using these tools with my students. Do you know if instructors from outside your university can get access? Well, that's a question that I will forward to Eli. I think we should be able to find a way to share these resources with you,
Yes.
but I'm not sure exactly what are the steps that you should follow.
Yeah, so these labs are available. Now, regarding like teaching in a course, just because the number of students would be typically large, we try to do it on a case-by-case basis. So if you can reach out to us, and then we can basically talk with you and then potentially provide you access to those. But we are not putting it open in a way that any instructor can just simply go and do it by themselves, just because of the limited resources. And with classes, I mean, you can go from 20 to 40 students, and we just want to make sure that everyone has access to these resources. So if you're interested, feel free to send us an email, and then we can follow up after the workshop.
Great, great. All right. Any other questions before we jump into the hands-on sessions? Perfect, perfect. Another thing that I want to show you in this environment is that you will have also the lab manual. This is very important, which is here under the content tab. This is the lab manual that we are going to use for this activity. And what I usually do, just to make sure that we are following the steps and we are consistent with what we do, I will undock this. And here you will have the lab manual on one side. Let me put it on the left, right here, and the client machine right here. So here we have the VM, and here we have the lab manual. And let me even undock this VM just to have more space, so the view is larger, so we can see clearly what we are doing. So that's better. You have also some, I like, for example, using the actual size, so it will reaccommodate to your screen width. All right, now let's get started. And I will show you how this lab manual is related to the hands-on activities that we're gonna do here. So, this is the lab manual. You have the content, you have the overview. Basically, if you're teaching a course and you wanna just have a quick overview of what we're doing here, or just wanna have a quick view on this lab, you just check this first part. Here you have the credentials. We just have one VM. In case you need a password, the password will be password, a simple step. Here we have the lab roadmap, and in section number 1 is where we provide a background on the activity that we are gonna do in this lab. Here we talk about, we give an introduction on dynamic routing protocols. We explain where BGP is located in this roadmap. Then we provide a BGP overview. And finally, in section number 2 is where we start with the step-by-step procedure in order to configure BGP. In this case, intro to BGP. Here we have the detailed version of the topology, where you have the IP addresses, networks, interfaces, and device names. all of these device names H1, H2, R1, and R2, they are related and mapped to a topology that we have in this VM. Then we have a table with the IPv4 and subnet information. And you can see that we provide the information in case you want to troubleshoot or configure something else on top of this lab. So you have the table here that could help you. And then in section 2.2 is where I will start with the step-by-step procedure. Feel free to do this with me or just follow, and in case you have any question, please feel free to post it on the chat as well. All right, the first step is opening MiniEdit. MiniEdit is a graphical user interface that we use to run Mininet topologies. You know, Mininet topologies by default, you should build it using a script, but we have this interface that will help us to create topologies or load topologies that we already created for this. The password here is password. You won't see the password while you type it. Just press enter. This is the Mininet environment. So let me, okay, perfect. Let me reaccommodate this screen a little bit. All right. Once we are here, on step number 2, what we're gonna do is loading the lab topology. And this is something that we do in all the labs. We just go to File, Open. Here you have all the labs that we have in this series and exercises as well. We're gonna click on lab number 3, open that directory, click on the lab topology. This is a .mn file. This will contain the Mininet topology. And this topology that we have here in Mininet is mapped to the one that we specify here. So should be consistent with what you have in this lab manual. All right. All right. So after you load the topology, you go to the terminal. I will click here on the icon. You will have the Linux terminal. And the next step is to navigate into this directory, BGP labs, and then lab 3. And here on step number 5 is where you run this script. And this script will basically do the pre-configuration steps for us. It will set the IP addresses to the interfaces. It will enable the required flags in order to forward packets and make sure that routing is possible. So we can just focus on the lab activity. The script is config loader.sh, and I will call this lab_conf.zip. This is the one that contains the configuration files for this lab. Let me check if I don't have any typo here. I think we're okay. That's all what we have to do here in the Linux terminal. You can just close it by typing exit. We're done. At this point, all the hosts interfaces, the IP address of this host and this router's interfaces, they are already configured. On step number 7, we just go to the lower left-hand side and click on Run. You can see that this part of the Mininet MiniEdit view will be gray out. That means that our topology is running. Now we can just check the links. On step number 8, you just click on this terminal that you have here. This is the Mininet terminal where you can run Mininet commands. That's explained in lab number 1, if you want to take a look. In this step, we are just gonna run the links command in order to see the links here. So let's make sure that everything is consistent. Here, for example, we can see this is the topology information here. We can see that S1 is connected to R1 through interfaces ETH1 and ETH0. And so it is for the other for the other elements or components that we have in this network for H2, S2, R1, R2, and so on. So here you can see that information. In the following step, let me show you also how to relate these interface names, which is a little bit different from what you see on a regular Linux, but believe me, it has like a logic behind. On this section, we are just gonna verify some information and load some configuration. Let me just open a terminal here on host H1, and here's where I will ask for your attention. If you want to open a terminal on host H1, you just right-click on it and hold it. Don't release it. You will have this prompt. Then you select terminal. You put your cursor on top of terminal and release it. In that way, you open a terminal in host H1. This is a mininet instance that is isolated from the operating system that is hosting this topology, and you can run any Linux command. You can see here, for example, we can run the ifconfig command. So we can see the interface configuration H1 ETH0. This is the interface that we use to connect H1 with switch S1 in this case, right here. You can see that this is the IP address of this IPv4 address of this interface, and also you have the other information related to IPv6, MAC addresses, statistics, and also you have the loopback interface here. Great. Now let's check the default route. We already in the configuration script that we ran in section 2.1, we configured the default route here, so you don't have to do it manually. So I will just run this command here and do it route. And we should be able to see something like this. We can see that the default route is through the router R1. So this is the IP address that we use to reach router R1, which is our default gateway for this activity. Now, on step number 4, we can do the same for host number 2. So let me just open and show you. Let's verify that the IPv4 address is configured. That's important. You can see 192.168.2.10, and then everything else looks good to me. We have a question here. Are we getting the recordings later? I am on transit and network is bad for me. Not a problem. You will see the recordings. They will be posted on our website. This is the workshop website. Let me put the link on the chat. And by the end of today, you will see the recording down here. So we are recording this and it will be available on this website. All right. Back to the lab. Now let's see what is inside the routers. On step number 5, I will just open a terminal on router R1. Again, you right click on router R1 and put your mouse or cursor over terminal, release it, and you are in router R1. And you will see that this environment is not that different from what you observe in host H1. The reason is because this is just a network namespace, which is like an isolated version of the hosting OS running on this environment, which is R1. All right, but now what we're gonna do is we are gonna initiate the instances that will help us to implement or to run the FR routing tool. And that first component is called Zebra. Zebra is a daemon, a multi-server routing software that provides TCP/IP-based routing protocols. This is basically the interface between the routing protocols and the forwarding tool. This tool is explained in more detail in lab number 2. Then, to get into the CLI, to configure the routes and see the routing tables, on step number 7, we are running PTY-SH. This is the virtual interface, and this is how we access the software router. Here you are in FR routing, you have the prompt, and from here, commands are different from what you see in a regular Linux because we are running this in the virtual interface. So let's run this command, show IP route. This will look familiar to you. If you're familiar with Cisco IOS, this is how we see the routing table. You can see that this information that you see here, you have the codes and you have the routing information. This should be consistent with the topology. You can see this is the directly connected network that is selected and preferred. 192.168.1.0/24 is the one that is directly connected, and 192.168.12.0/30 is directly connected here. Basically, we are seeing, let me refer to the topology up here. We are seeing these two networks. This network and this network are directly attached to this router R1. Something similar we are going to see on router R2. Let me just make sure that I'm following the steps. On router R2, let's do the same. Open a terminal. We'll run the 0 daemon. I will access the router software routers interface, PTY-SH, and run show IP route. As you were expecting, you can see that we have two directly connected networks, 192.168.2.0/24 and 192.168.12.0/30. These are two networks that are directly connected to router R2. Perfect. The good thing is that everything is configured, everything is ready, so now we can start with BGP. In section number 3, we show how to enable BGP and configure it. Well, let's take a look. Let me refer back to router R1. I will just go down here on the taskbar. I will select R1, and here I am. I will exit for a while from the FR routing virtual interface, and here back to the Linux instance, I will enable the BGP daemon, which is what we do here on step number 2. BGPD, that one will enable the BGP daemon. That daemon is running. Let's get back to the virtual interface, PTY-SH, and here we are. Now, let me just, to make it a little bit clearer, let me Control L it. It will clean everything. And even I will enlarge this. So we just focus on router R1's configuration. And here we move to a global configuration mode. We run the configure terminal command. And then after we are there, we enable the BGP configuration to operate with the autonomous system number 100. So let me run router BGP 100, and now I will configure the BGP router. I will establish a router ID by running this command right here. BGP router ID, let's call it 1.1.1. And then I will configure the neighboring information, or in other words, I will establish how router R2 will be reachable from router R1. And this is very simple. We use the neighbor command, and we specify the IP address of router R2, which is in this case is 192.168.12.2. And then we specify that this will be the remote autonomous system 200. Note that we haven't configured yet autonomous system 200, but we are specifying here already. Oh, I think I have a typo, so sorry for that. So neighbor.
It should
Oh.
be remote rather than route.
My bad. Thank you. So the command should be remote a-as 200. That's it. Good. That's all what we have to do to configure to peer to BGP neighbors. Let me end this. So we are back. And now let's verify BGP neighbors. We are going to run the following command: show IP BGP neighbors. And here we can see the neighboring information, such as the IP of the neighbor, the remote autonomous system, the local autonomous system. The remote router ID is 0.0.0 because we haven't configured that yet, but our local router ID is 1.1.1. We set that one. That's a BGP router ID. We will also see the statistics about the BGP peering information here. We haven't established a connection. You can see here connection established is 0. So this is something that we have to do in router 2. So we can see some statistics popping up here. All right, let's make it work then. We move to router R2 and we follow the steps right here. Hopefully I don't have a typo now. Router R2, let me enlarge it. I will exit because we have to start the BGP daemon on this router. Then we get back to PTY-SH. We go to global. And we configure router BGP 200. Perfect. We set the router ID, BGP router ID 2.2.2. And we also specify how we are going to reach our neighbor, which is router R1. 192.168.12.1. Here remote -AS 100 in this case. This will be the remote AS, and that's all what we have to do. We establish we configure the neighbors now. Now let's verify the BGP neighbors table. In router R2, let me run this command: show IP BGP neighbors. And you can see that down here we have connection established. We go up. You can see some more information. You have the remote router ID, local router ID, the state of the connection, which in this case is already established. You have the running time and many other statistics that are related to this BGP peering. All right, now let's do an experiment. On router R2, I'm here already. Let's ping router R1. Let's see if we can reach router R1. You can ping here as well. Let me clean this, Control+L. Ping 192.168.12.1. That's router R1, and you can see that router R1 is reachable. Now, from router R2, let's try to ping host H1, which is ping 192.168.1.10. And you can see that the network is unreachable. Why is that? And the reason is that we configure the BGP peering between router R1 and router R2, but we haven't advertised the networks that are attached to these two routers. So that's something that we have to do in order to enable end-to-end connectivity between two BGP routers or devices that are in the local networks. All right, let's get back to router R1. and we're going to advertise those routes. This is what we're going to do in this section. Right. From the taskbar, router R1, and let me clean this, Control+L, configure terminal, and router BGP 100. So configure this router. And here is where we use the network command to specify the networks that are attached to this router, and we want to advertise in order to enable connectivity. We are going to advertise network 182.168.1.0/24. Let me check. Yeah. And that's all. That's all what you have to do here. Let me end this, and we are going to verify now. If we go to, we are already here in router R1. Now let's see the BGP table. We are going to show the BGP table, show IP BGP, and you can see that we have the BGP network that we just advertised, which is this one, and that's all what we have to do here in router R2. We are going to do the same, or move router R2. We are going to verify routing information. In this case, we're going to show the routing table with the show IP route command. And you can see that we have a new entry here. Besides the two directly attached network that we had previously, we have another one, which is 192.168.1.0 on router R2. This is the network that we just advertised in router R1. And you can see that it has the prefix B here. That means that that route was learned via BGP. And I think in the following step, we're on router R2. We're going to verify the BGP table. All right, show IP BGP. Oh, you can see that in our BGP table, we have the external route, which is external prefix, which is 182.168.1.0/24, and you have the next hop and the other metrics. Let's do the same on router R2. Remember that in router R2 we haven't advertised the network that is attached to this router. So let's do it very fast on step number 8. Configure terminal, and then we are going to do router BGP 200 network 192.168.2.0/24. So we advertise this network, and that's all. Type N, and that's how it works. BGP table on router R1. Let me clean this. Show IP BGP. And you can see now our BGP table contains the information of prefix 192.168.1, and the local network, which is 192.168.2.0/24. All right. Finally, we are gonna verify this information, or we're gonna check the routing table on router R1. Show IP route. Let me clean this even. And you can see that we have the 192.168.2.0/24 network reachable, and that was learned via BGP. As a final test, we're gonna go back to host H1, and we're gonna try to ping host H2. So let's see, here I have host H1. Let me clean this. We'll ping 192.168.2.10. So you have it here. And you can see that the end-to-end connectivity was enabled via BGP. We can do the same from host H2 just for the sake of completeness. Let me go to host H2 and ping host H1. And you can see that we can reach host H1. All right, and that's it. There you have it. This was the basics of BGP. I hope you find this interesting. This is a very basic lab. There are more advanced ones, but the goal here was to introduce you to the platform, to the tool, and show you the way we develop these labs and the way that we are showing these steps and to illustrate everything that we want to make. All right, so we have questions here. We have interaction in the chat. I don't know if there's something else. I will stop here. I will stop sharing my screen and see if there is something else. All right, here we have a very nice interaction. I'm trying to relate all the steps with other routing protocols to understand better. No passive interfaces are needed to be declared on R1. I don't think passive interfaces on BGP, I think that's something more related to OSPF, which is what I think Ali was explaining down there. By the way, let me share back my screen. And we cover also other routing protocols, although it's not part of this workshop. Let me just refer to the website and show you here in the cyber training tab. You will see all the materials that we developed. We have P4-DPDK, which is covered in day number 2, but we also have a very nice library on OSPF. We have the virtual labs on OSPF, and here is where we cover all the things we configure. We use OSPF version 2 and also OSPF version 3 that works with IPv6. And this library is available for you upon request. And yeah. All right. Another question. In the mininet topology, is it possible to see packets flowing from one node to other graphically like in Cisco Packet Tracer? Unfortunately not, but let me explain the difference. With mininet, what we are doing, we are treating this as real traffic. This is what we are generating with mininet is real traffic, meaning that we are not going to have that step-by-step procedure as in Packet Tracer, because Packet Tracer is a simulator. It follows a mathematical model in order to reproduce the network behavior. And on the other hand, here on Mininet, we generate real traffic and we handle real traffic. Something that you can do with Mininet, and that's something that we show in some labs, is to use Wireshark. In Wireshark, you can just capture the packets and see what's the content and do your analysis there. It's not exactly as you have in Packet Tracer, but it's something that is useful. You have 2 different flavors there, so that's what I can add to that point.
I would also add, it's more, in my opinion, at least, it's more flexible in the sense that it is running on a real Linux stack, and all the tools, everything is the same as what you would see in real deployment. So if you are interested in using something like TCP dump, or as Jose mentioned, Wireshark, or you need to do scanning, any type of command available in Linux, you can run it there. It's just because you're inheriting the commands that are available in your Linux machine onto these network namespaces. So more testing can be done over something like Packet Tracer, where you just have basically like very few services available that you can play with.
Yeah. And also something that we usually do, not for the labs, but for our experiment, is to create mininet topologies. And bridge the interface, a real interface to a real device. So that's something that you can do with Mininet as well, because you're working with real traffic, so you can just use real devices within your Mininet topology as well. All right, let me see if there are any other questions, comments about this great interaction. Great, so as you understand, we can do things we can't in Packet Tracer, like measure latency. That's great. Yes, actually, we have a lab series. Oh, I'm sharing my screen. That one is a very nice lab series. It's called Network Tools and Protocols. This one is a very comprehensive lab series on Mininet in the same environment, but here we show how to, for example, use iPerf, how to use NetTem, network emulator, to set latency, jitter, packet loss, packet duplication, reordering, and corruption, so we can like emulate real scenarios, problems that occurs in real networks, and many other things. So this is something that we also show in these labs. All right. So we have another question here based on your presentation. Can BGP be used for redundancy? I think Ali will have a demonstration on that with some redundancy with hot and cold potato routing that will be covered in session number 2. If you want to add more on that, Ali, I don't know.
Yeah, sure. So yeah, you can have like multi-home networks where you're connected to, for example, if you're a customer or your campus network, you can be connected to multiple ISPs. The first one, like you can have a primary path and the secondary path. The primary would be like the where your traffic would typically go if everything is normal, and if like maybe a link failure happened to the primary, then you can seamlessly switch kind of to the secondary ISP or other networks. So we will have in the next session, we'll have a kind of two links between two different autonomous systems. One of them would be like primary, the other would be secondary. So yeah, to basically answer your question, that's very possible.
Yeah, if you want to learn more how to steer traffic, how to set some preferred or secondary paths, as Ali was explaining, I think this is something that we can do with some BGP attributes as well, such as local preference and multi-exit discriminators. These are activities that we cover in lab number 8, 8.1, and 8.2 respectively. Yeah. Is there any other questions or comments?
All right. Thank you, Jose.
Thank you.
I will share my screen again to go over the agenda. So we just concluded the first hands-on session by Jose, and hopefully this gave you an idea how to get started, how to navigate through the environment, and how to start a simple network and perform simple configuration there. So what we will have now is a short break, a 10-minute break, and then we will come back at 2:30 p.m. Eastern Time. And next, George would be talking about local preference and MED. And after that, there will be a lab, a hands-on session lab, similar to the one that Jose did. It will be executed by Ali. And we're going to see how to basically test those knowledges in practice. So again, let's come back in a little bit more than 10 minutes, 13 minutes. So we'll come back at 2:30 p.m. I'll just put this one here. And meanwhile, if you have any question, the chat is still going to be open. Feel free to ask there. Thank you.
BGP. BGP care and feeding is a very important factor. So BGP can just work in most cases, and it needs tuning for optimal or desired performance. Quite often, BGP out of the box in simple situation just works. As we saw in the lab, we had A and B just talk. Best path selection, and you'll notice the table on the side there, is a 10+ step process, and it goes through these discriminators. Steering mechanisms are how network engineers tuned for best or desired path behavior. So let's talk a little bit about this BGP steering. Here are a few BGP steering mechanisms. So there's access control lists, there's AS padding, there's local preferences, there's MED or multi-exit discriminator. Oh, excuse me. There are communities, there's preferential import and export, there's route reflection, and these are just a few. Let's start with ACLs, access controls list. These are the most basic filtering mechanism and can be a trivial form of security. You can permit or block routes based on criteria such as source, destination, origin type, AS features such as length, if it exists, and so on. It does require careful consideration and review for care and feeding to avoid unintended impacts. Example being, you can adjust an ACL or an existing ACL and create a routing loop. You could black hole traffic you didn't intend to black hole. You need regular reviews and careful considerations before you implement or modify your ACLs. AS path padding. So as we recall, BGP will choose the shortest path. We had that diagram with the top path that was 100 gigs and the bottom path that was only 3 hops. Well, we could pad it. Padding is done by adding extra ASNs to the path attribute in the BGP update. Just lengthen it out. This can be used to influence incoming, traffic, exit points, or routes into other networks. Add 1 or more copies of your AS number to prefixes to advertise to specific neighbors. And then there's a trivial example there, and the bold are where the ASN 133465, that particular AS's update, involved 3 copies. That is now a longer path. Local preferences, and a lot more detail on this in just a second, but this is one of the steering mechanisms. It's used to state the relative desirability of a particular route within an AS. So this is in your autonomous system. The higher local pref is preferred, the lower is less preferred. Local preferences are used per prefix. So this is a flawless tool for keeping RNE traffic on RNE networks. So an example here, we have a local, and we set a local pref of 200 to RNE next hop or peer, and a local pref of 100 to our regular commodity ISP. As you can see, because the local pref for the RNE pathing, let's say it's our science DMZ, or let's say it's a supercompute cluster trying to talk to another supercompute cluster. In this situation, the local pref, we want to steer towards that RNE path. Thus, the higher value, and it is preferred. The local pref would then have you not transit the commodity to up, over, and get to that RNE destination. Multi-exit discriminator, or MED. And again, there will be a lot more on this later. This is just, again, another high-level overview. BGP selector that is used to state the relative desirability of a particular exit route to a neighboring AS. So in other words, you get to say, hey, peers, here is where I would like, or I ingress, egress. This is how I exit. This is how you can ingress. This is backwards, right? Lower MED is more preferred. Higher MED is less preferred. And this is exquisite for redundancy. So example being, here we have in our primitive diagram, a regional ISP represented by 2 geographical locations. So regional ISP A in green might be the west router, and ISP A purple might be the east router. Well, we know that west happens to be a little bit further or a different hop, or there's reasons that we do not wish for the traffic to transit that way from our regional ISP. Maybe the green ISP is multiple kilometers away beyond what was reasonable for latency. So we prefer to have our exit path updated to the purple. We would set our med to 4, and we'll notice the purple regional ISP A then gets the preferred path in versus the med of 12 on the other, which would not be preferred. Communities. BGP community strings are tags that can be applied to prefixes and inform specific behavior to other BGP routers. Prefixes can have multiple community strings, provide information about prefixes, and can inform peers of local preference changes. They can be used for something as simple as DDoS mitigation. Always look upstream for published communities. So example, here's a look upstream. If you were to peer with Energy Sciences Network, we would have these communities. And you'll notice we have 51 for ESNet connected sites, 52 for research and education networks, 53 for commercial networks. It's our ASN paired with the community. Preferential import and export, or traffic engineering. Creating traffic policy by crafting routes based on preferences such as origin, AS path, communities, IBGP, or eBGP, internal, external. Preferential import and export allows for fine-tuning of specific routes and TE strategies. So you can do a lot of traffic engineering with preferential import and export. And route reflections. So let's say you're a very large network and you want to bring down some of the communications or some of the sessions that are necessary. Route reflection is exquisite and excellent steering mechanism in this situation. So intermediate routers, so you can have a few more routers that reflect routes in order to reduce the overall number of BGP sessions required to exchange routing information between routers and an AS. You can dial the conversation down. In short, a method to reduce complexity in very large networks by lowering BGP conversations. Security was mentioned, so I'll say a few words about manners. So the joke is mind your manners. Manners stands for Mutually Agreed Norms for Routing Security. It is a global initiative that helps reduce the most common routing threats. It was created and intended for network operators and internet exchange operators. You guys can see the link there, and when you have the slides, please click this, explore it, enjoy it. Well, Manners provides a set of routing and security best practices and guidelines. There's a lightweight certification. And its mission is to try and get a critical mass or herd immunity for things like anti-spoofing, prefix filtering, anti-hijacking. Matter of fact, the original author of the slide, it was mid-COVID, so they put a Manners COVID mask on. Major components for network operators and service providers also, such as prefix filtering, prevention of propagation of incorrect routing information, anti-spoofing, coordination and communication, and route validation and route policy expressions. Manners in R&E and with partners. So here's a few examples. Hopefully you'll see your institution or know of some of the institutions you see on here. There's even out in some of the cloud areas participation in Manners. It is truly a great community to get involved with and work with. So a closer look at BGP local preferences. I was joking with my son, I'm like, what icon would indicate a preference? Well, I choose you, Pokemon, so thus I chose Pokeballs. So, local preferences. Used to state the relative desirability of a particular route within an AS. Again, the higher local pref is more preferred, and the lower is less preferred. Local preferences are used per prefix, and again, as mentioned before, this is a great tool for keeping R&E traffic on R&E paths. Again, back to the same example. We have an R&E path, we have a commodity path. Local pref lower, don't want to go that way. Local pref higher, I want to go that way. Local preferences are a very nice coarse adjustment. The local preference attribute is carried between BGP updates between routers within the same AS. So you notice that's the second one down on that chart there. A higher local pref indicates more preferred path. Again, lower, less preference, and less preferred. The default is 100 frequently. Oh, yeah, matter of fact, I didn't even mention that on the next slide. Depending on the OEM, the local pref usually defaults out of box to a value of 100. If multiple paths have the same value, so you have an out-of-box router, another out-of-box router, the value of the next policy established criteria goes next, aka we would take a look at, like, say, the MED or shortest AS path, or you could go down this list and see where the match works. So there's caution that comes with local preferences. So local preference settings are not shared beyond the local AS. Peers do not see your local pref values. That's your local preferences. While high on the decision list, local preferences are best used in harmony with other steering mechanisms, some of the mentioned ones earlier, or say policies like multi-exit discrimination. So let's look at multi-exit discriminator, or MED. I tried using a discriminator knob off of, say, a metal detector. So this is the refresher again. The key takeaway here is the lower the MED, the higher the preference, the higher the lower. This is flawless for redundant routes. So we have a redundant route to a regional ISP. It's the same ISP. There might be 50 ISP routers of that regional. We can have a MED set for each. We could have regional east, west, midwest, northeast, southwest, depending on how your network is laid out or how your peering is set up. It's a way to inform the remote autonomous systems where the preferred route is. It's a great steering mechanism for redundant or multi-router connections to a remote AS. When combined with local preference routing, it can cover ingress and egress for multiple paths to appear, or appear with multiple route ingress egress points. It's, again, an excellent tool for having RNE peers choose the most desired route to you. MED values are passed in BGP update conversations. So back to that wonderful question about TCP dump. It can be a tiebreaker when other attributes are identical, i.e. local pref is out of box and it's matched with another default. It's best used when other steering mechanism policies in that MED values can be ignored by, or, oh, apologies, hang on, let me read that properly. Best used with other steering mechanisms and policies. In that, the MED values can be default and will be ignored by remote AS peers. So, by default, remote AS peers don't necessarily respect or value your MED. It can, though. Like all BGP policies, they require frequent review and careful consideration. Ooh, interesting. Wow, that is my last slide. Do we have any questions?
Is can we check if our ISP or internet network provider participates in manners? Is it online? We can check it.
Oh, that's a great question. I am not sure on that. One of the things I'll recommend, and matter of fact, when we're doing BGP peering, or even when I was in a former institution, job -1, job -2, one of the best things we did is became excellent friends with our upstream providers. Our network engineers and the ISP, our upstream ISPs, were constantly talking. We had a great, literally, we would go to lunch together or we'd have coffee together. It was one of the ways we were able to help forge out a dedicated RNE network at 100 gig, and this is back in 2014, 2015, directly into our data center pathing. Our network engineers worked with us, and we were able to walk through security best practices, had basic, excellent jam sessions. To be able to determine if a particular remote that you're not direct friends with is in or involved in manners or not, I do not know out of the gates. I apologize.
I was just interested there, but yeah, I know the website, so I might have to do like some research on that because it's very interesting, and I don't think there's like a lot of research on that. But it's from practical side. I've been saying that it's very recommended nowadays.
It is. They do have a participants list, and I'll put the link there. It does seem very extensive. I don't know what to happen or what would happen if your organization is participating manners and not listed there. I would imagine you'd need to contact the group and go from there. But I don't know. Let me see if hey, Energy Sciences Network is in there.
Yeah.
Let's go for let me see if my old institution is in there. Several universities are listed. That's nice to see. I'm trying to think of another one. Let's try. Ooh, Google's mentioned. Yeah, use the link. Take a look. Enjoy.
Yeah. I'm
Yeah.
checking it right now. Thank you.
All right, thank you. That was a great presentation. If there's any question, again, please feel free to post them in the chat, or you can unmute yourself and speak. I will go back to the agenda real quick. So we just finished the local preference slides. We finished a little bit earlier, 10 minutes earlier, but that's fine. So we can start right away with the hands-on lab, and this will give us enough time if we need more time. But I see now that there's a question if George or Ali wants to address it in the chat.
I love that question. It depends on how mature the setup is, and it would depend on your desired state. So if it's an out of box, you could have local prefs that are default at that 100 value or whatever is out of box. And you could decide to engineer and steer via med only if you have a redundant connection to your next hop. Yes, lightly. Both of them would fall through on a tree of selector where local pref is higher. Let me share screen just for a split second.
Sure.
And I'll go back to the slide deck and I'll go to that table. And apologies. So local pref are versus, it goes weight, local pref, and med is a little bit lower. So if your local pref was 100, and say your AS path of path A was, for example, 5, and the other AS path was, say, 20, that would have weight in the decision tree. Then the med would come in and have lowest. So you need to be aware there's multiple selectors here, and I believe we'll cover that pretty extensively here in a bit.
Right. Thank you. Thank you, George. All right, so the next session is gonna be a lab, and this is gonna be ran by Ali Al-Saba. Ali is an assistant professor at USC ACAD. So Ali, you can take it away from here.
Thank you. Just to confirm, you can see my screen, right?
Yes.
All right. So just to comment on the last question. So just comment on the last question that Ronald has asked. Basically, and I will show you maybe if we have some time at the end. In this lab, we have multiple. If I go to the cyber training website, so okay. Yeah, we have several labs. Some of them actually cover when you need to configure local preference attribute and how does that affect basically the network steering and when you need to configure MED. So for example, in this lab number 8, we configure both of them in our network so that the incoming traffic and the outgoing traffic both get influenced because we have to keep in mind that the local preference affects everything that gets out of our local autonomous system, and the med attribute affects everything that's coming inside our autonomous system. And as George was mentioning, there's a priority for the attributes, so which is basically this best path selection mechanism. So I'll jump to my presentation, but I omitted that because George was talking about it earlier. But essentially, when BGP selects the best path, it has to go over a set of criteria. So first, it will check the weight, which can be manually assigned. And then, for example, it checks the local preference. If this is equal, then it moves to the next criteria. If this is equal, it moves to the next criteria. So there's like a set of steps that BGP follows for the best path attribute. All right, and gonna start with just a quick presentation about the hands-on session. And please feel free to interrupt me and ask any question. So for the BGP best path selection, as George was mentioning, there is a set of criteria that BGP goes through. But most commonly, if we don't do any configuration for BGP, if we don't do any specific attribute configuration to be more precise, what happens is that the most common reason for AS path selection is to prefer the shortest AS path value. So what is this AS path value? Essentially, when you're advertising BGP attributes, let's say that network 1 will advertise, AS100 will advertise network 1 to network 3 and network 2, right? So when network 2 wants to reach network 1, after it gets this advertisement, it will follow the path, which is this one, from R2 to R1 directly, because the AS path attribute is shorter. So it needs only one hop or one autonomous system to reach network 1 from this way, whereas it needs 300 and 100, which is 2 to reach network 1. So this is the case where typically we don't have any BGP configuration. It chooses the shortest AS path value. Now, if you have multiple paths to the same destination, and they have the same length, so you can traverse the same number of autonomous systems to reach this destination. So in this case, the BGP path selection mechanism will work as follows. It will check the MED attribute. So if other neighbors have sent you a MED value, the more it's preferred, so you will take that. And if this is equal, the MED attribute, so if we didn't configure it, so BGP typically prefer external BGP over internal BGP. So the peer will always prioritize sending traffic to its external BGP over IBGP. So it kind of tried to get rid of the packet outside its autonomous system as soon as possible. Okay, and here we're talking external BGP is some peer that's outside our network, outside our autonomous system. So this is what we refer to as hot potato. So the packet, sometimes we refer to it as a hot potato in which the packet gets out of the nearest egress interface from our autonomous system. Now, this is kind of like a normal BGP behavior. The network typically can manipulate this behavior. So sometimes you don't wish to have hot potato routing. So you can modify this using the local preference attribute, as we will see in the lab. Now, just to illustrate this hot potato routing, let's take this example. We have two ISPs, each one of them is in a different autonomous system, and we have customer 1 on this side and customer 2 on this side. Now, if we just configure BGP without any complicated BGP attribute manipulation, customer 1 will send traffic to customer 2 via R1, R3, R4. Why? Well, here you have to look at it. You will see that both links, there's only the AS path attribute is the same. So you look at the MED, there's no MED, and then you will look, this from here is through eBGP, and this from here through iBGP. So BGP prefers routes advertised via eBGP, so it will take R1, R3, R4. It's not gonna take R1, R2, R4. Okay, and that's what basically R1 will try to get rid of the packet outside its autonomous system immediately. Similarly, from customer 1 to customer 2, R4 can either send it through R3 or send it through R2. No, it will choose R2 because this is the prefers eBGP or over iBGP. So it will also throw the potato, quote unquote, into R2. Now, this is the normal behavior, and this creates routing asymmetry. So what is routing asymmetry is that when the path taken from the source to the destination is different from the path taken from the destination to the source. Okay. Now, sometimes this routing asymmetry is not, it has its advantages, but it also has its disadvantages. Some of the disadvantages it can cause is performance variability. So maybe the throughput on one path is different than the throughput on another path. You also have some troubleshooting complexity because you have to deal with multiple path nows. You also have introduced security risks. In fact, like sometimes the firewall will be configured on a certain port, not on the other port, so this will create some security risk. Now, cold potato routing is the opposite of hot potato routing, in which the autonomous system retains the packet or the traffic as long as possible before sending it to the next autonomous system. So in this case, for example, if we are configuring cold potato routing in AS100, then R1 for packets from customer 1 to customer 2 is gonna stay in autonomous system as long as possible. So it will go from R1 to R2, and then from R2 it will jump to R4. And this is what we refer by cold potato routing in AS100. So if we kind of have a combination of hot potato routing in AS200 and cold potato routing in AS100, then in this case, we will achieve routing symmetry. And an example, why would you choose to keep your packet or traffic inside your autonomous system as soon as possible? In fact, Google sometimes do that, or major content service providers, because they are confident of the performance that they have in their data centers, and they don't want to sacrifice this performance, so they will keep it as long as possible inside their network. All right. So this is just a introduction about hot potato routing and cold potato routing. So let me just introduce to you lab number 12, which is configuring hot and cold potato routing via the BGP local preference attribute. This is going to be our topology, similar to the example that we had. Initially, all the links will have a capacity of 10 gigabits per second between the routers and the host. But one thing is that R1, the link between R1 and R3, which is this link, has a packet loss of 0.1%. So as we know from hot potato routing, or the default behavior of BGP in this scenario, is that traffic from network 1 to network 4 will go H1, R1, R3, R4, H4. And coming back, network traffic from H4 will go to R4, R2, R1, H1. Now, this first creates asymmetry, but it also causes throughput degradation. Why does it cause throughput degradation? Well, because traffic that's are going through R1, R3, and we said that it has 0.1% packet loss. So in the lab, we will verify that, and we will see that the throughput is not 10 gigabits per second. It's actually much less than that because of the packet loss. So, and also we will trace the route with the initial BGP configuration from H1 to H4 and from H4 to R4. Now, what we're going to be doing is that we will kind of transform this hot potato routing into cold potato routing in AS100. So on R1, I will configure the local preference attribute on, in Autonomous System 100. I will go to R1 and I will say that, hey, the link R1, R3 has a local preference value of 50, but the link between R2 and R4 has the local preference 75. Now you have the two ways that you can reach from ISP1 to ISP2 are tagged with the local preference value. And we know that the higher local preference is the better or the more preferred, and this local preference will be shared among IBGP peers. So R1 will know, all right, I'm no longer gonna consider R3 to be the next hop for traffic to network 4 or AS400. No, I'm gonna use router R2 to send the traffic. This is the local preference configuration that, again, it influences the autonomous system. It's the routers within the autonomous system, not something external. Now, after we configure this, we will notice now if we do a trace route test from H1 to H4, then this is going to be the path that it will be taken. H1, R1, R2, R4. And of course, the coming back from H4 to H1 will remain the same, which is in blue. Now, once we do that, we will do a performance test again using iPerf, and we will see now that cold potato routing on AS100 and hot potato routing on AS200 basically allow us to have a routing symmetry where the path that is traversed is actually produces a 10 gigabits performance. So basically, this will be the hands-on session that we will be doing. Now, I have a question. Which is better, the cold or the hot potato routing? Well, it really depends on the. I think it really depends on the provider or the autonomous system itself. So, for example, what I was saying, the example of content service providers such as Google and Meta and others, they sometimes prefer to keep the packet as long as possible inside their autonomous system or network because they can guarantee performance. So in this case, maybe cold potato routing is preferred. And another case where maybe the network performance or maybe there's a lot of congestion in this transit network, for example. So the transit network will try to get rid of the packet as soon as possible by just throwing it to the nearest egress point. So hot potato routing would be preferred in this case, but it also has some like security risk. So I think that's my take on it. But if some other people that has experience with the network operation want to add on that, please feel free to do that.
I can add in a comment on the hot potato, cold potato. it depends on the paths too. So let's say you have higher bandwidth on a specific path, or your regionals may be at a farther distance and you span that last mile. If it improves science or improves your mission, go cold potato. Hang on to that traffic as long as you can. If you have unpreferred traffic or, like mentioned, high congestion, get it off the network. It becomes a hot potato. So definitely, I agree with the answer. It depends.
Thank you, George. All right. So let me get to NetLab. Again, if someone can post a NetLab link on the chat so that I'm just using because I'm in kind of like within USC network. So I'm using the IP address instead of the link. Okay, so I'm gonna schedule a lab for myself under lab number 12. So it's called hot and cold potato routing. And if you don't find any available pod here, you can click on the arrow again. Let me choose one random one. You have to click on the red line. That's important so that you can proceed with the lab right now. And I will enter my session. Okay, so the beauty of this is that every lab is has a content and it's self-contained. So if you have students or even if you want to learn about this on your own, you can check the content right here. You can undock it if you want to follow the content and the lab each on one side. Okay, and every lab is self-contained. So even if you don't have much knowledge about the topic, such as hot and cold potato routing, local preference attribute, you will see an introduction about that here so that you get familiar with it. Since we already talked about that in our presentation, I will skip the first section. This is all about theoretical concepts of what we will be doing. And now another thing is that the next section is going to be about the lab topology, which is the following, the one we said in the presentation. And this is the lab settings where we have like the IP addresses. So let me go ahead and open my topology by clicking on the client right here. Okay, I'm just gonna wait maybe 1 minute so that 1 or 2 minutes so that everyone, all of you have their reservation. And meanwhile, if you have any question, please feel free. All right. So we're gonna be using mini edit to emulate the network. And file, I'm gonna load the topology by file open and then lab 12. Okay. Select the topology, so you will have the topology already configured for you. You don't need to do any configuration for that. And in addition to that, I will be loading the IP addresses on the host and the routers. So to do that, I will have to run the script, open a terminal, change the directory to lab 12, and execute the script config loader, and we give it the configuration file of lab 12. So here we make sure that we don't really need to do the IP address configuration for this lab, and then we exit. All right. Now, once we load this script, we can run the topology by clicking on the run button right here, and it will be grayed out. Now, again, let's say that you want to verify the links, you want to see which interface is connected to which node. So you can click on Mininet terminal and you can write links. And here you will see every interface, every node and interface connected to every node and other interface. All right, so far, let's first, if you want to open a terminal on host H1, so you hold the right click on H1, click on terminal, and you write ifconfig. This is a completely separate namespace for every host, every router, every device. And here you will see that the IP address is already 1.0 based on our topology, based on our table. You can also verify the default route on H1 by writing the route command, and it takes like a few seconds, but eventually it will tell you that the default route for H1 is router R1. So we have that configured right here, gateway 1.1. Now, the first step is that we were gonna be loading Zebra on every router so that the IP addresses are actually loaded into this router, the ones that we configured using the script. So hold the right click on R1 and then launch run Zebra and then VTYSH to log into FRR shell. And then after that, now it's it's a Cisco like iOS. You can write show IP route to view the connected directly connected routes. Here on R1 we have 3 directly connected routes. Again, if you go back to the topology, this is one for H1, one for R2, and one for R3. Similarly, I will open a terminal on router R2. So hold the right click and terminal and Zebra VTYSH show IP route. Again, you have to load Zebra and you have to load the daemon routing daemon such as BGP or other routing daemons on every router. It's not enough to just load it once because again these are in their separate namespaces. And here you can verify the routing table of router R2 has 2 directly connected networks. Again, there's no routing protocol configured yet, so that's why you will see only the C code, which stands for directly connected network right here. All right. Now, similarly, on router R3, you have Zebra VTYSH, show IP route, and to verify that. And finally, you have, we do it on router R4, Zebra VTYSH, show IP route. Okay. All right. So for section 2, we're done. We we loaded the topology, we loaded the IP addresses on each of the hosts as well as the routers. Now the next step, or which is section 3, is to configure BGP on the routers. So we configure regular BGP where each router will peer with its neighbor. So for example, R1 will peer with R3 and R2, and each router will advertise its directly connected networks. Let's see how we do that. Let's go to R1. Okay, and let's first, to enable the BGP daemon, we have to exit to the Linux terminal and write BGPD. So this enables the BGP daemon so that we can do BGP configuration. Now the next step is to go back to FRR through vtysh command. And now what we do is we go to the configuration mode, so configure terminal. And this is where the BGP configuration starts. So router R1 is in autonomous system 100. So you write router BGP 100. Okay. Now the next step is that it's a good practice to assign a router ID for your BGP routers. So what we will typically we refer to them as like for R1 1.1.1.1, for R2 2.2.2. So this facilitates the BGP communication. BGP. This step is not necessary, like it's not gonna stop the BGP peering, but for viewing our neighbors, it's better. All right. Now the next step is to router R1 has two neighbors, R2 and R3, that needs to peer with. So how does it peer with R2? Well, you will write the neighbor command. So my neighbor is router R2 has the IP address 192.168.12.2, and router R2 is in autonomous system 100. So remote-as 100. And you can also use the tab to autocomplete some of the commands. Similarly, router R1 will peer with router R3 using this command, neighbor 192.168.13.2, remote autonomous system 200. Because router R3 is an autonomous system 200, so we have to specify the autonomous system that it is in. Now, the next thing is that router R1 will advertise its network. So this is network 1, which is 192.168.1.0. How do you advertise it? Well, it is through the network command. So network 192.168.1.0/24. Okay. Now, in addition, for every router here, we will advertise all directly connected networks. So R1 will advertise this and 12.0 and 13.0. So let's advertise 12.0 on R1. Network command 192.168.12.0/30. Be careful with the subnet because it will not work if you have a wrong subnet. And finally, we will advertise 13.0, which is the link between R1 and R3. And we can exit now the BGP configuration. And all right. Now this right here will basically summarizes the whole BGP configuration. On R1, simple peering between your BGP neighbors and simple network advertisement. All right. Now, the next step is that I will need to do the same thing, but on different routers. So now I will move to step 13, which configures BGP on R2, and it's all summarized in one screenshot. Let me open the terminal on R2. Let me clear this by Control L and exit, enable BGP daemon, go back to VTYSHFRR shell, configure terminal, router BGP 100, because that's where the autonomous system of R2. R2 has a BGP ID 2.2.2.2, and R2 will pair with R1 and R4. So R1 is 192.168.12.1, remote autonomous system 100. R4 is 192.168.24.2, autonomous system 200. Also 12.1, 24.2. Okay, and R2 will advertise this link 12.0 and this link 24.0. 68.12.0/30, network 192.168.24.0/30. And we can exit the BGP configuration mode. Let me double check the configuration. Okay. Now moving on to router R3. Same thing. R3 is an autonomous system 200, so router BGP 200 has router ID 3.3.3.3. It's like an IP-like address, 32 bits. R3 will pair with R1 as the IP address 13.1, an autonomous system 100, and R3 will pair with R4 that has the IP address 192.168.34.2 in autonomous system 200. And R3 will advertise network 192.168.13.0, and R3 will advertise 192.168.34.0/30. And we can end the BGP configuration. Now the last router is router R4. Same thing, scroll and follow the steps. Zero and all right. With this, basically that ends our BGP configuration on every router. Now, the next thing is that I will, in section number 4, I will set and verify the BGP local preference on R1 and R2. But before that, let's actually see the behavior of the network traffic going from network 1 to network 4 and coming back. So let's verify the BGP configuration and the hot potato routing scenario. Let's go back to R1 and write show IP BGP to display the BGP table on R1. And let's see this specific entry in particular of our interest. So this tells us that router R1 can reach 4.0/24, which is network 4, through 2 next hops. The first next hop is 13.2, which basically 13.2 is R3, and the second next hop is through 24.2, which is through R2. Now, which one is selected? You can know from the arrow, which tells you that this arrow right here is for the next hop 13.2 or router R3, and you can see the status code as well here. So the arrow means this is the best next hop that will be installed in the routing table. So this tells us that router R1 sent traffic to network 4.0 through 13.2. Now, and another thing is that local preference is not set, or it's set to the default value of 100. So there's that's why you will choose the eBGP or over IBGP. Now let's display the routing table on R1, and from there we can see that we can validate what we said earlier, that 4.0 is reachable via BGP. Now the code B appears, and this is basically reachable via 13.2, which is the router R3. Now let's do a trace route from H1 to H4. Open terminal on host H1 and do a trace route. And see what is the path taken from H1 to H4. Okay, so the first next hop is 1.1, which is the default gateway on H1, which is R1. The second hop is 13.2, which is router R3. The third hop is 24.2, which is router R4. And finally, from router R4, it will go to host H4 that has the IP address 4.10. Okay, now this is the way from H1 to H4. What about the way back? So now this is hot potato routing established in AS100. So on the way back, I can open router R4 terminal and do the same validation. So show IP BGP, and I will verify that 1.0 is actually reachable via this entry, or basically 24.1, which is router R2. And you can verify that using the show IP route command, which is essentially tells you that 1.0 is reachable via 24.1. So this is the actual entry that's installed in the forwarding information base, or the FIB. You also have other BGP entries that were advertised. These are like the local links, direct links between the routers. Now, again, we can do a trace route from H4 to H1. Okay, so the first hop is 4.1, which is the default gateway. The second hop will be 24.1, which is the nearest egress point in autonomous system 200, which is router R2, so from R4 to R2. And then it will go to 13.1, which is router R1, and finally it will go to H1. Now, this asymmetry between the source destination and destination to the source, let's verify that, let's see the internet throughput that's basically induced from hot potato routing on these two autonomous systems. So I will run iperf on H4. So this allows me to launch iperf as a server, and I will open host H1, and I will run iperf as a client, and then I will send traffic to 4.10. let's see the throughput in this column right here, the bitrate. You will notice that despite that we said that all the links have 10 gigabits per second capacity, the throughput actually goes down to a few hundreds megabits per second. The average is just 1.2 gigabits per second. Again, why is that? Because traffic from R1 is going to R3 and this link has packet loss. So here in the next section is we need to configure local preference in autonomous system 100 so that R1 send traffic to R2 if they are going to autonomous system 200. Is there any question? Like just to pause a little bit to see if anyone has any question, or am I going too fast? Correct. We are converting hot potato routing and autonomous system 100, which is this one, to cold potato routing so that it will follow the path taken in the orange or the red. Instead of taking this path, it will take this path using local preference attribute. Yes, correct. So our whole goal was to avoid using the lossy path R1, R3. So yeah, eventually we'll see much improvement in the throughput, and we'll do the experiment again after we configure that to verify. Yes. All right. So let's continue. Let's go to router R1 back, and let's go to the configuration mode, configure terminal, and to configure local preference, we need to establish a route map. So this route map will allow us like a access control list that you can match on a certain criteria, and then it's like match and action. And then you can permit and deny. In our case, we're going to create a route map on R1 called secondary N, and we will permit traffic with a sequence number 10. Okay. Now, when you have more complex route maps, you will have more sequence numbers that goes from, it's like if condition, that's based on priorities. Now, our route map will have a local preference value of 50. So set local preference 50 right here. And the next thing that I will do is I'll just exit this route map. So now I define the route map and I apply the local preference attribute. But the thing is that on R1, you have to apply this route map to a neighbor. So I will log into BGP. So, BGP configuration, router BGP 100. And I will assign this route map secondary N to my neighbor 13.2. Okay, let me do it and then show you what's actually going to happen. So one neighbor 192.168.13.2 route map secondary N and then N. So what this command does is that any advertisement that basically you attach the neighbor 13.2 to this route map, okay, and then you specify the code secondary N that we described we defined here. So now at the end of the command, there is an in, could be out for med attribute, for example. So this will apply the policy for incoming traffic, or like, yeah, incoming advertisements. So now in this case, anything that's coming from R3, which is basically information about network 4, will be coming from R3, will be matched with this secondary in. There's no match, there's no specific criteria, so everything will be matched. And then the action would be to set the local preference to 50. Now, the advertisement that's coming from R3 to R1 will have the local preference of 50. Now, what I need to do is that if I want R2, R4 path to be chosen, then this path should have a higher local preference attribute, R2, R4. How do I do this? Well, I need to log in. Let me just 13.2 and secondary in. Okay, now let me go to router R2. Which is here. And let me configure terminal, route map, primary, and permit 10. So this will create another route map on R2. And by the way, the route maps, even if it's the same name, the route map are separate. It's local to the router itself. So, but we are just calling it primary N because we need this path to be primary. So just like for readability, on R1 we called it secondary because we needed R1, R3 to be a secondary link that's only used if the primary is not used. So basically, this goes back to the initial question about redundancy, where basically we have BGP configured with multiple paths, and the primary is used, and the secondary or the lossing path will be used only if the primary is not used. So the same thing, I will need to set the local preference attribute to 75, and then I'll exit. So whatever value you set it, you have to be greater than the secondary. So we just chose 75. And then we go to the BGP configuration, 100. And we establish a peering with, not establish a peering, sorry. I assign this route map to neighbor R4, so 192.168.24.2. The route map is called primary N, and then I specify N at the end. So here, all the advertisement that's coming from R4 to R2 will be assigned a local preference value of 75. All right, so this is basically the local preference attribute configuration. Is there any questions so far? So the question is that wouldn't that overload the link between the autonomous system and degrade the overall network? So you mean the link between the autonomous system? Well, okay. So yeah, this link will have all the traffic loaded, but this link has 10 gigabit per second capacity, which is and doesn't have a packet loss at all. So we would rather prefer to have this performance over that performance, which is through R1, R3. So there are other techniques to do like load balancing, but we don't like cover it in this lab. But you don't want to have load balancing in this scenario if you have like a robust link that can be 100 or 10 gigabits per second, you would prefer that all the traffic go through it. Yeah, we're taking it as a perfect scenario. Yes. Thanks for your question. All right. Now let's verify the configuration that we did. Let me go back to R1 and let me see the BGP table. So show IP BGP. Let's consider this network 4.0. So again, this network 4.0 still has two routes or two next hop, one through 13.2 and one through 24.2, or basically R2 and R3. Now you notice that the difference now is that this arrow right here, this arrow changes from up 13.2. Now it's pointing to 14.2. It's pointing to 24.2. So now it's telling me that this network 4.0 will take the next hop 24.2, which is router R2. Why is that? Because the local preference of the next hop 13.2 is 50, but the local preference of the next hop 24.2 is 75. And we know that the higher local preference, the more it's preferred. Previously, both of them had the same local preference of 100. That's the default local preference. So BGP will move to another best path selection criteria, which is in this case eBGP over iBGP. Okay. Similarly, like not only network 4.0 is being advertised, but also if you see the network 24.0, which is basically the link between 2 and 4, this will basically take 12.2 as a next hop, okay, which is router R2. But our focus is on the traffic coming from the customer, which is 4.0. Now let's do IP routing, show IP route. In this case, what does the IP routing table tell us? On R1, the IP routing table tells us that there is a route learned via BGP, so the B code. This route is 4.0/24, so this network. This has the administrative distance 200, so okay, 200 is the administrative distance. And now kind of also goes back, if you have multiple routing protocols such as OSPF and others, of course, between autonomous system, that's not gonna matter because, but within the autonomous system, IGP is preferred over BGP. Now this network is reachable via 24.2, which is R4, and R4 is reachable via 12.2, which is R2. Now I can verify that whatever has been installed on the routing table or forwarding information based, it kind of conforms to the concept of cold potato routing that says that packets will stay as long as possible within the autonomous system before they go outside. Okay, so now cold potato routing is established in AS100. Let's see if AS200 has been affected. So router R4, show IP route. This case, we have 1.0 is reachable via 24.2. Okay, so interestingly here, we kept hot potato routing in running in AS200 so that the blue arrows or like the blue route is taken. And this tells us that the local preference attribute is local to the autonomous system and it's not something that's advertised outside, like such as the mid attribute. If ISP2 if network 1 wants to influence the traffic coming from ISP2, then you would need to configure med attribute, and we have lab number 8 on that if you want to do it. All right, so let's do a trace route again from host H1. One 192.168.4.10. Let's see if the cold potato routing is in effect. Okay, router R1. Router R2. And should be router R4 and H4 eventually. And this is R4, and finally you have H4. Okay, that's great. We verified cold potato routing. The last thing that we want to do is to perform an iPerf test, which is essentially our goal is to improve the performance by having routing symmetry along a specific path. So on host H1, I will do an iPerf test. And here I will verify that the throughput is actually 10 gigabits per second. Right? So basically this ends lab number 12 on hot and cold potato routing. Please, if you have any question, feel free to unmute yourself or write in the chat. I will be looking here to see any insights you have, any recommendation. Please feel free to do that. Thank you.
All right, thank you, Ali. I don't see any questions. If there's any question, Ali will be here, so he can still answer. Just feel free to post them. Back to the agenda. So we just finished the second hands-on session. So this is the one that Ali just did. For now, we have a break. We finished a little bit earlier. So instead of having the break from 4 to 4:10, we can have it from now, 3:50 to 4. So we can come back at 4 and start with the Science DMC. I will put this here. Let's put it at 4. Again, the chat is open. Feel free to send your questions there.
Let me go ahead and share screen here. So in this section, we'll be talking about designing, building, and maintaining a science DMZ and data architecture. I'm a guest speaker on the slide deck. I've seen this presentation several times and I always enjoy it. So I hope I do it justice. Doug sends his regrets. He really wishes he could be here today, and I hope I can present as well as he would have. So the outline: introduction, solutions base, and conclusions. What we'll be talking about, and one of the parts of science DMZs, is a mindset adjustment. When we talk about network, we're usually talking about infrastructure. We're talking about the switches, the routers, the cables, the point A, point B, here and now. We need to start adjusting as a community to think of the network as an instrument or part of the instruments. Example being, ESNet has the whole philosophy of we need to be able to get data from the Hadron Collider over to major institutions. We need to experiment with data that may come from the JWST all the way up to things at Fermilab. There's bigger and bigger and bigger major facilities coming online, and we can participate. We can help enhance that. You can participate. You can help enhance that by creating the most optimal science DMZ possible and keeping the paths in the community well-informed and enabling science. Connectivity is the first step. Usability must follow. So, the solution space and understanding these solution spaces, preliminaries, architecture and design, and then we'll dive into the next parts and the conclusions. So the common theme will be a new mindset. We're not building a new network architecture, and we know how to do this. We've been doing this. We know how the internet works. These labs have shown us there's great ways to get routers to talk to routers. What we need to think of when we start getting into the science DMZ and the data transfer is the data architecture. A lot of items that'll be thrown a bit at you transcend the traditional network space. And part of that might be, how do you move data sets that are in the petabytes? How do you get from cluster A to instrument B real time? How do you get the researchers and the science flowing in the best possible result to keep it friction-free, to use a term? We need to understand, and to get there, we need to understand the data pipeline. We need to know cradle to retirement home. We need to know the target use case and the users. We need to know point A to point B and what happens when we place our hand on each section of those diagrams. This implies all the things: the creation of the data, the usage, how it's processed, where it's processed, why it's processed, transfers, shares, permissions, security, curation. What are the results? You can think in genomic space. Some of the files start out really tiny. When they're in the compute phase, there's peta, tera, exa, and then it drops back down to results and maybe a final published paper. Then again, back in the mindset, what you build must be usable, defensible, scalable, and institutional capability. And it's, again, a great source of pride. So usable, it can't be a walled garden. Make it so that people can easily hop on board and get integrated into work. Defensible, it shouldn't be, oh, anything goes here. It's not the Wild West. Control the users and use cases, but don't impact the usage. Scalable, again, as demand grows. Think along the Lego brick toy. Can it get bigger? Can it go? What would be the best possible outcome? An analogy is, think cornfields and baseball diamonds. If you build it, the researchers will come. And then the source of pride and the institutional capability. Is this something that will draw more users? Will it integrate more research dollars? Can it be marketed? If it's operated correctly, treat it as such. Make it the best it possibly can be. Here's kind of the example to let us all go around this whole science concept, right? So there's development of service, there's planning capacity growth, and there's creation of collaborations. Within each of these on the Venn diagram, you may have a networking team, you may have a compute team, you may have a storage team. They all generate data. We have algorithms and software. Algorithm software could even capture an AI. This is only going to expand and get more and more. And the network is only a subsection. The storage, a subsection. The compute, a subsection. They all must interact elegantly and provide the best possible platform for your researchers and for the scientists. So preliminaries, and these are some of the networking protocols. So data movement and the way the internet and machines work is based on TCP. TCP is the transmission control protocol component of TCP/IP. The data mobility performance requirements for data-intensive science are beyond what can typically be achieved via normal transfer methods. Default host configurations. You defaultly install an Ubuntu or a RHEL or a Cent or a Rocky or any type of operating system. Most of the configurations out of the gate are defaults. File systems are tuned to be vanilla. Network cards, vanilla. The operating system manufacturers and the OEM manufacturers want defaults because they want those boxes to work when they power up. Converged network architectures are designed for commodity traffic. There's no advanced tuning put on the converged. They want, again, for support perspective, it to work. Conventional security tools and policies, they can be blunt, and again, they can just work. Legacy data transfer tools, again, packet A to packet B, but not necessarily what we want when we want data movement. SCP, FTP, when you compare that to something like Globus, you could have months of difference in transfer when you compare the defaults to the best possible scenario. And then also even the support. You think about how when there's a research environment or a scientific environment, you don't sit around and wait for trouble tickets or operational models. You need to be performant now. You need to be proactive. You need to be seeing what's next, what's on the horizon. TCP, Transmission Control Protocol. It's ubiquitous and it's fragile. Networks provide connectivity between hosts. Well, how do hosts see the network? From an application perspective, the interface to the other end is just a socket. Communication is between applications, mostly over TCP. Congestion is where there's a performance lever. It backs off when danger is sensed to preserve the network and protect resources. Hey, are you there? Are you there? And then back off. Ask a little slower. There's many algorithms in this. And we consider TCP kind of a fragile workhorse. For good reasons, it's timid. Packet loss is interpreted as congestion. Packet loss, in conjunction with latency, is an absolute performance destroyer. Like it or not, TCP is used for the vast majority of data transfer applications, and literally more than 95% of ESNet traffic is TCP. Here's a fun graph that we love to show. This is an older graph, and on the y-axis, we've got throughput, and then on the x-axis, we've got round-trip time in milliseconds. So notice the top line up here. This is optimal and measured with no loss. So this, there was a mention in the chat earlier during the previous presentation, the optimal situation. This purple line is as optimal as we're able to get on a 10 gig link. So something interesting starts happening right around 10 milliseconds. And if you think about time, and you think about the speed of light, and you think about the speed of light through fiber, now we're looking at that 10 millisecond distance. This is right where WAN starts happening. Data center is 2 milliseconds or less. So you're up in here if you're top of rack or in data center. You start getting maybe around in here if you're building or cross campuses. When you get beyond, you start getting into massive, massive areas of regional or continental or international. So these are a couple of, you can see the drop off, and this is with 0.0046% packet loss. There's a lot of things that can happen and go wrong. You can take a 10 gig link down to a 1 gig link at roughly 12 millisecond distance. With high loss, high performance is beyond metro is essentially impossible. You could do it, but why? Let's fix this. We have a lot of options in our toolboxes. So data movement and our TCP background here. So the Science DMZ model describes a performance-based approach. It's dedicated infrastructure for wide area WAN data transfers. It's well configured. It has extremely well configured and performant transfer hosts known as data transfer nodes or DTNs with modern tools, very capable network devices, high performance data path, which does not traverse commodity land. So again, we can think about the R&E network versus the commodity network. You know, a short path may not be the best. Proactive operational models that enable performance. So example being along the lines of proactive monitoring and proactive performance tools. One of them is PerfSonar. It's a point-to-point continual testing option. So example being in the previous labs, we used iPerf3 to show the retransmissions and the bandwidth. PerfSonar can schedule that and run that continually in the background, in addition to throughput, latency, and many other options. PerfSonar is an exquisite tool. Periodic testing, which it does, it locates issues instead of waiting for that user to complain or that ticket to be raised. And then also a security posture that's well matched to high performance science applications. So example, remember one of the steering mechanisms is ACLs. You can say commodity, go away, or hey, campus, let's try and adjust the way where our border router is versus the campus border router. Or if they're the same, maybe we talk and have how we tune our local prefs or meds. So here's a science DMZ in one slide. We have the example of what friction, the true definition from an engineering perspective is. So it consists of 4 key components, all of which are required. A friction-free network path. Again, highly capable network devices. We're going for wire speeds. We're going for deep queues. We want virtual circuit connectivity options. A to B, A to C, A to K with no problems. Be able to instantiate it at will. Meet the needs of the science, meet the needs of the researchers. Security policies and enforcement specific to science workflows. If it's going to be an elephant flow and you're dumping grid FTP or Globus traffic and it's going to be transferring peta for a month, I doubt you want a firewall inspecting every packet. You know that that's going to be a true elephant flow. Let it go, let it pass, let it get that data from A to Z as fast as possible. And then located at or near site perimeter as far on the edge as possible, if possible. Again, dedicated high performance data transfer nodes, the hardware, the operating systems, the libraries, the software, the tuning, all optimized for speed. Get the NIC as busy as possible, get those disks as busy as possible, light that fiber up. This includes tools optimized for transfers such as Globus, Grid FTP. There's many tools that are designed to help make a transfer more modern than rsync, SCP, FTP. And then again, I'll recall out PerfSonar. And know what your users are doing. You're trying to go from A to Z. Know the data curation, know the path, ask them, help tune the path. And then again, I'll call out fasterdata.es.net. We have a science DMZ pattern, and I'll call out a couple of the photos in here. All of this is well documented on Faster Data. The fun part is, this is science DMZ in one slide, but yet when you think about researchers and human nature, this is more of the reality, right? We've designed this beautiful, absolutely amazing path for them to walk on. Yet you see a researcher carrying a box of hard drives across the dirt, across campus. Why? Sometimes it's a fundamental friction to entry or integration. Don't do the hardware in the science DMZ just to do the tools and the sysadmining. Do it to be able to enable the science. So don't forget the mindset change. Perhaps when designing, the designers were flawed. They needed to look at the path that the user experience had created. So in the architecture and design, let's take the science DMZ and acknowledge it has many forms. There are a lot of ways to combine all of it, and it depends on what you need to do. One of the best answers when talking about science DMZs or even science or research in general, the best answer is it depends, right? Could it be a small installation for a project or two? I can think of a project where we're just trying to get accurate time from a telescope to another telescope. There's maybe one fiber and 2 devices involved in the whole setup, but it's helping the research get to that next level just by answering and asking a few simple questions of what are they trying to do? Maybe it's a facility inside of a larger institution. Maybe it's institutional capability serving multiple departments or divisions. Maybe your institution has a light source, or maybe your institution offers something that no other institution in the region offers. Now you have an option to have interconnectivity via your science DMZs and your networking pads and your R&E networks and your regionals that can bring that jewel that your institution provides out to the rest of them. And then again, science capabilities that can consume majority of the infrastructure. You might have something like, let's say, a small Hadron Collider instead of the Large Hadron Collider. When that does a shot, it's putting petabytes on the wire instantly. That can saturate. That can be a very different design parameter versus the small installation project or two where it's just a light source and a light source. Some of them are obviously straightforward. Others are less obvious and require deeper dives and or knowledge of where the data goes from A to B and all the paths in between. Some of the key points definitely are look for where packet loss potentially could occur or does occur. And packet loss truly is friction. The simple iPerf3 and hot potato to cold potato lab we just did is a perfect example of what a network engineer may do to help alleviate flow or science flow issues. We noticed that one leg had packet loss, the other leg didn't. Perfect use case. The R&E network can be optimized. Legacy method that's used is the ad hoc DTN deployment, right? So love this graphic. The stitch plan ahead, the D never actually fit. So this is often what gets tried first. We want to do data transfer. Okay, let's go buy a server. Okay, well, how much does it need? I don't know. Let's just throw some disks at it. Okay, let's install some sort of Linux and let's throw it on the network placement and let's just stick it in the racks and see what happens. That might not be as successful as possible if you were to think about, oh, we need to get this much data from A to B, and we also have users in Z that need to get to B. Maybe we need more disk. Maybe we need multiple DTNs. Maybe this area of the network isn't quite optimal. The ad hoc method, it's easy to turn on, but it's very hard to achieve performance. If lucky, and there was a little bit of planning, or a network engineer, or maybe you or somebody else that's forward thinking had put a Personar node at the border, it's a good start. You can at least get some metrics and start measuring. And then maybe you need a second one next to the DTN. The entire LAN path has to be sized for the data flows. The entire LAN path is part of any troubleshooting exercise. So when you think A to Z, institution A to institution Z, that LAN segment is critical when you're factoring in the WAN performance. It could be any hop along that path. So we think back to how R&E networks are built and designed. They're designed for performance, throughput, and their open architecture. You should be able to ask and know everything in that path. And again, back to ad hoc deployments, it usually fails to provide necessary performance. So here's a graphic, ad hoc deployment. Researcher grabs a DTN node. It's great. It's tuned. It does everything it needs. It has NVMe storage. It's on the best building connection possible. But then it has to hit a top of rack switch somewhere in the closet. Then it has to go all the way through campus, multiple buildings, campus backbone, a couple of firewalls, maybe a couple of different VLANs. Then it finally gets to your perimeter firewall and maybe your edge router. Goes through the network cord. Maybe an IDS is there, maybe a logger is there, and then finally it gets to the site border. You might have Personar out here, and then it gets out to the traffic. Just the DTN to the router, the number of hops in here is not necessarily fixed, definable, and traceable. So here's a simple DTN pattern. This is a science DMZ, and it's a simpler approach. Well, let's get out of campus. Let's get into a research network. Let's design this for clean bandwidth. Let's make this go as fast as possible. Let's keep it secure via access control lists. And then let's make it optimized. So you'll notice the low latency LAN path. This is so that this can be stewarded, managed, configuration management can come in. It can be a control plane, for lack of better terms. So from campus, you can invoke change upon this. And the only thing that this node is able to be exposed out to the border router is a research and education route. It's a clean high bandwidth path. This may be on the 100 gig or 200 gig optic network connection, all the way straight into the DMZ router switch. Your perf sonar has that 100 or 200 gig connection, and it's able to test out to the WAN perf sonars. So you can test this switch, you can test this switch, and you can test this switch, and you can definitely test between these two. So you know every single path there is from your segment. Now, when the remote site says, hey, we're seeing slowness, you can say, hey, can you hit this? No, yes, okay. Can you hit this? No, yes. And then it's a simple flow chart to what the most optimal path or where the issue is. Here's an expansion. So we can add in dark fiber for each individual project. Each individual project can have security controls. So you have your DMZ switch or router, whatever device is most obvious or necessary for use. And then you can take advantage again of ACLs or routing paths, where project B is never able to interact with project A unless it is explicitly allowed on the paths. Again, the pattern is expanded. We have the test points. We're able to cross-check anything that's needed, and security is here. We're not making this a Wild West situation. We would never have a researcher put a laptop in here unless it was part of the security research plan and it was well documented. Here's even more expansion. Let's say we're talking clusters to clusters and grid compute or grids of storage. Maybe this is Luster. Maybe this is high performance energy cluster. Maybe this cluster, facility B, may be running a cluster that is genomics. Maybe this cluster is collaborating with this cluster. So there could be a path to and from. The admins and the research proposals or the sites may be running on the campus themselves. They should be able to go in, out, and be able to test as necessary. Likewise, friction-free to any one of these paths with test points. So routers and switches. The requirements for Science DMZ gear are different than enterprise gear. There's literally a kitchen sink worth of services that enterprise gear can come with. You don't necessarily need that. A Science DMZ box only needs to do a few things, but it needs to do them extremely well. They need support for the latest LAN, or correction, support for the latest LAN integration magic with your Windows Active Directory environment is probably not super important, to say the least. A clean architecture is more important. How fast can a single flow go? Are there any components that go slower than interface wire speed? If so, why is this switch or equipment worth it? There is a temptation to go cheap. I've seen folks where they're like, oh, we're on a shoestring budget. Well, sometimes shoestring budgets get you shoestrings. It only needs to do a few things, right? So you typically, you don't get what you don't pay for. Sometimes you don't get what you pay for or what you don't pay for either. So make sure it meets your needs. Have a test plan in place. Don't hesitate to have a perf sonar on a remote site and a perf sonar on this site. Let the data drive the decisions. Common circumstance, multiple ingress data flows, common egress, right? So background, inbound, we see that whole diagram on the right there. Hosts will typically send packets at the speed of their interface. Instantaneous rate, not average rate. So if TCP has a window available and data to send, the host sends until there's either no data or no window. So hosts moving large data i.e. those large DTN servers or those well-tuned DTN servers can send bursts of back-to-back packets. This is true even of the average rate measured over seconds, say 4 gig, 5 gig. On the microsecond timescales, there's often congestion. So router or switch must queue packets or drop them. So what we're getting into is interface queues, i.e. buffers. So output queue or VOQ doesn't really matter, right? What TCP sees is what matters. Think like the packet, be the packet. Know where the packet is flowing, storing, forwarding, or is it flowing and going? So what TCP sees is truly what matters. Fan in is not your friend, and fan in isn't buffer bloat. So have good counters. We like the ability to count every packet associated with a particular packet flow, like address pairs, how it behaves. It's insanely helpful when it comes to debugging packet loss. Your flows and your measurements must not affect performance. Just count it. Don't do fancy things with it. And then SFlow support if possible, right? If the box is going to drop a packet, it should increment a counter somewhere indicating that it dropped the packet. You want to know, like we go back again to that comment, in an optimal situation or a lossless network, we want to be as close to that as possible. If we're not, we want to know about it. We want to know why and where. Some magic vendor permissions and hidden commands should never be necessary. And some boxes just lie. Don't buy them. Single flow performance should be wire speed. Excuse me. So again, let's look at the buffer, and this is a no cut through example. So we have all our input links, and we have input buffers. Here's the packet selection function. Then we have a routing function. Then we have a packet dropping function as output buffers. So input links and output links, right? So data arrives from multiple sources. It comes in. Buffers have a finite amount of memory. Some have this per interface. Other may have access to shared memory regions with other interfaces. So that's also important in hardware selection. If you can find a block diagram or have your vendor or OEM provide you even a high-level block diagram of how the ASICs are laid out, how the processing occurs, where the hardware acceleration occurs or doesn't occur. The processing engine will extract each packet frame from the queues, pull off the header information to see where the destination should be, move the packet frame to the correct output queue. Additional delay is possible as the queues physically write the packet to the transport medium, i.e. you needing to write to that ASIC or you write into that optical, the optic itself. Or a copper interface. Let's say you're optically clocking up or down. Let's say you have a QSFP and you only have a 10 gig link. Or I know we all have in our network kit those 10 gig SFP plus to 1 gig adapters. That can do delays. So again, on buffers, the bandwidth delay product. How do we calculate how much buffer we need? I'll answer out of the gates with it depends. So here's an example, again, referencing that initial chart we had where we saw at 10 milliseconds, it dropped off, right? So let's think about cross country or about 100 milliseconds. We run the math here and we're looking at about 125 meg of buffer that we would need. This is the amount of in-flight data for TCP connection. So ignore the math entirely. It's nice to see that we can run this and we can get a ballpark range. So let's say you want to do this for 100 gig. Let's say you want to do it for 800 gig. Let's say you want to do it for terabit. You can run the math. But it's making sure there's memory to catch and send the packets at all hops. Otherwise, you instantly have the equivalent of a fire hose, coffee cup straw, fire hose. That little coffee cup straw will become quite a problem because it doesn't have enough buffers. As the speed increases, there are more packets. If there's not memory, they hit the floor. We drop them. And that makes TCP react. And of course, the researchers are not happy. So buffering isn't as important on the LAN. This is why you're usually pressured to get a top of rack switch or a cut through or a small home and office special or whatever gets the job minimal viable product done. Keep in mind with research, science DMZ, and science, this is a little bit different. Run the math. Make sure that the latency is 1 millisecond and the expectation drops by 2 decimal places, right? So if we do a cut through and low latency switches, you're fine at top of rack. 10 gig top of rack, no problem. Send, go. We're good. The instant you get to that 10 millisecond though, or just outside the metro area, buffering matters and matters a lot. So we're thinking WAN transfers, right? We've been talking BGP. The instant you get into the external BGP and you start talking your border to the regionals or the further regionals or whoever you're peered with, you're instantly talking, what are your buffers, what are your sizes, and we're at the WAN layers. WAN wide area network. Placing something with an inadequate buffer in the path reduces the buffer for the entire path. Again, think of that coffee straw, that little tiny straw versus the 2 fire hoses. If you have an expectation of 10 gig over 100 milliseconds, don't place a 12 meg buffer anywhere in there. You don't want it top of rack. You don't want it down the hall. You don't want it anywhere. And that goes back to that first ad hoc where somebody placed it in campus. The top of rack switch in the networking closet might be 12 meg, might. It's just trying to get to the next building or the building's route. So the reality is now 10x, a factor of 10 less than it was before. So you're getting a gig at 100 milliseconds. Here's an example of congestion control. So 50 millisecond simulated RTT, and this is a single stream throughput through a congested Arista, and throughputs versus retransfers versus current Windows sizing. So we can see the bumps and the hops, and it's quite a ride. Notice that the throughput here in gigabits per second, and notice the retransmits. So in iPerf3, think of that retransmit column, right? We saw when there was packet loss, the retransmit incrementers were higher. This is a graphical representation. Keep in mind, this is an example of a graph that is presented via perf sonar. So all that wrapped up, data movement is hard to get right. DTN from facility A to DTN facility B. Think about the paths, lots of moving parts. You've got everything from operating system selection to software selection, the types of servers, spinning Rust versus NVMe, networks, and don't forget people. People are part of the network. Testing reveals that some of the above may not be ideal, and testing will also motivate you to make it ideal. Shared experiences around the community lift all the boats and share the knowledge. So example, if the collective, anyone in here is doing something or building a science DMZ or coming up with a new way to do data transfer, share, let us know, participate in local conferences, have talks, don't hesitate to reach out, be vocal, because things that you do that are novel or innovative will help everyone and help make science better. So overall, thanks again for having Epic. We love talking on this topic. I think there's a lab coming up on congestion control. And if not mistaken, I think I read ahead and saw that BBR might be mentioned. It is an exquisite protocol. The Epic Help Desk I'll bring up here. We love looking into science DMZs, data flow patterns, tuning. I personally love tuning servers, coming up with performance methods and tweaks. Don't hesitate to reach out. Let us help you. With that, I do not know if I'm ahead of schedule again. I think we may have had a little bit of extra. Nope, that was the end. I am happy to answer any questions, and go from there.
Thank you, George. That was a great presentation. Yeah, this is really summarizing all the main parts of Science DMZ. And as George said, it's very hard to get the performance right. I mean, there's a lot of points that has to be looked at, tuning the end host, make sure we have enough buffers, make sure we have a clean path. There's a lot to be done there to get that 10 plus gig that you want to have for your researchers. So for now, we will not gonna do any more labs just because of the time. However, I'm gonna be showing you some of the practical stuff that relate to what George was talking about. So this is a demo here, just showing data transfers and showing the impact of packet loss on TCP. So first, this is Fabric. Fabric is a test bed that is across the US, and there are also connections to other countries as well. And with Fabric, you'll be able to select different sites that you're interested in, and then you'll have a terminal there. You reserve the resources, you select how many CPU cores you want, how many RAM, and then you'll be able to run experiments. And these are all 100 gig links, so you'll be able to run a lot of the experiments that would be very useful to test before you can deploy it on your network. So for this demo, I'm just using the Fabric testbed to showcase the impact of packet loss on TCP. So we have here a server in Washington, DC, so that's server 1. And then we have another server in PSC, Pittsburgh Supercomputing Center. So you can see the distance between these two servers is small. And that's what George also was talking about, like the RTT. What is the distance between two nodes? And the more far the node is, the higher the RTT and the lower the performance. The third server is in Los Angeles, and this is 70 millisecond round trip time from Washington, DC. So the packet to go all the way there and come back. So now here is just to show the terminal for each of the servers. So we are here in the Washington, DC server, that's server 1. I will run a ping test from Washington, DC to Pittsburgh Supercomputer Center, and you can see the round trip time is short, around 6 milliseconds. That's good. Now, if you try to ping to LA, this is gonna be around 69 milliseconds, so much higher round trip time. So the next step would be, well, let's see how much performance we get. If you are trying to send a data set, how much bits per second can we get? Now here, this part is basically setting the TCP congestion control algorithm. So also it was mentioned in the previous presentation that there's a lot of algorithms running to determine what is the sending rate at a certain point in time. And one of the congestion control algorithms used by default in Linux is Cubic. So Cubic interprets packet loss as congestion, and therefore it tries to react to that packet loss by decreasing the sending rate. What we are doing here, we're using this sysctl command. This is just a way you can tune kernel parameters. So here I'm saying I want to specify that the algorithm to be used is Cubic. Then I'm going to use iPerf3 here just to run a throughput test from Washington, DC to Pittsburgh Supercomputer Center. Remember that the distance is short, so we have here around 6 milliseconds. We are getting around 13 gig. It's going up a little bit. Performance looks good, right? That's what the link support here in this testbed. So the average around 13 gigabits per second. These two sites again have 6 millisecond round trip time. Now, if we try from DC to LA, which is the 70 millisecond round trip time, you can see how the performance goes down. We're getting around 6 gigabits per second. Notice when we got some retransmissions, then the TCP back off, and then the throughput went down a little bit. So now it starts to, if you remember that sawtooth shape that George showed in one of the figures, you are seeing it here. It goes up, then goes down, and then you wait, goes up, and then goes down every time you have packet loss. So the average is around 5 gigabits per second here. Now, remember that this is under good conditions, so maybe there are some packet losses through the network, but nothing crazy. Like there is no fault anywhere, right? So we are considering like a good snapshot of the network. Now in this step here, we will be injecting some emulated packet losses, artificial packet losses. And the rate is very small, 0.0001%, like a very small amount of packet loss being injected. After we did that, we're gonna rerun the test that we did before. So from Washington, DC to Pittsburgh, you can see that it went from 13 gigabits, now down to around 3.5, goes up a little bit and then goes down, but on average, maybe around 3 gigabits per second. Keep in mind that the distance here is short. I mean, even with 6 milliseconds and this small amount of packet loss, the throughput went way, way lower than it was before. But now if we try to LA, which has the higher RTT, you can see now we are in the megabits per second scale. We went down from 5 or 6 gigabits down to hundreds of megabits per second. And that's again showing you the problem of having high latency and you have packet losses. In those cases, the speed is going to be very low. So transferring a terabyte or petabyte data set, that's going to take forever. Take a lot of time for it to be completely transferred. So what are some tunings that could be done? One of the newer congestion control algorithm, different than the default one provided in Linux system, it's called BBR. This is an effort by Google. So BBR does not take packet loss as a signal of congestion, or it doesn't only take packet loss as signals of congestion. So it's not as sensitive as other congestion control like Cubic or Reno or HTTP or others. So if you see here, we set the algorithm to BBR. Now we can see even with the packet loss being there, we are getting 16 gigabits from Washington, DC to Pittsburgh. So you can see the retransmission count here is high, much higher than before. But because BBR is not sensitive to packet losses, we are still getting good performance. On average, over this 20-second test was 15 gig. Now, testing to LA with BBR and the packet losses, we went up from hundreds of megabits per second to around 5, 6, 7, all the way to 10 gigabits per second. Again, this is a very simple command. We just changed one of the parameters in the Linux kernel, and you can see the improvement in the performance. Now, there's way more parameters to be tuned. For example, what is the send and receive buffer sizes on the TCP devices? We're not talking about routers, just the senders, like DTNs, they have TCP limitations in the buffer sizes. You have to tune them, right? How many parallel streams can you use to maximize the performance? And there are others as well. So with that, what I will show here, just a few slides showing you some of the libraries that we have developed that are related to Science DMZ topics. So the first one is called Network Tools and Protocols. In this lab library, we have 22 labs, and it's one of the earlier libraries that we developed, but it's very comprehensive. So it would start by, first, if you want to emulate delays or emulate packet losses, similar to what I was showing in the demo. So you will learn how to do that with tools like NetM. How can you limit the link bandwidth, right? So if you want to put like a bottleneck of 1 gig or 5 gig, 10 gig, then traditional congestion control, so Cubic, Reno, HTTP, and then the newer congestion control like BBR. What is the relation between the bandwidth delay product and the buffer size on the DTNs? So here, this BDP is what also George was talking about, that 125 meg that was for the scenario of 100 gig and 100 millisecond, right? So how can you calculate that? Given a certain round trip time and given a certain capacity, how can you get a good amount of buffering to tune your end host so that they can get the best performance? Parallel streams, meaning that with the single data transfer, how can you leverage multiple TCP sessions? That has a huge impact on the performance. how can you measure fairness between flows? If you have 2 flows sharing the same link or 10 flows sharing the same link, how can we quantify if our system is fair? So you will get basically a measure between 0 and 1. If that value is closer to 1, it means that your system is fair. If you have 10 flows, means that, for example, and the 10 gig link means each flow is roughly getting 1 gigabits per second. The buffer size on the router, this is one of the key elements that you have to look into to have good performance, and what George was also describing. What is the best buffer size? What is the impact of incrementing the buffer to a large value or having a small buffer size? And there are other more advanced topics. For example, how can you play with the queuing disciplines there? You want something like CODL to control the delay, or you want to do fair queuing, and so on. So all of these labs are available already. So if you go back to your net lab and now you do a new lab reservation, there, in addition to the BGP labs, we added additional libraries. One of those libraries is this one here, Network Tools and Protocols. So you'll have access to all those labs and you can run them by following all the steps and basically completing the whole experiment. Another lab library that we have related to Science DMZ is PerfSonar. So this was one of the important topics that also was discussed related to how can you try to identify where is the bottleneck, where is the performance issue happening, where is the packet loss happening in the network, right? And PerfSonar is a tool that would allow you to find those, what we call soft failures. So the network is still running, but you're not getting the best performance out of it. So we have a lab library on that. 10 labs. So you start first by just introduction to Mininet, all the way till you schedule different tests, for example, throughput tests or latency test, or having a trace route test so that you can determine what is the topology looking like. And how can you visualize the measurements on a dashboard like Grafana? And this lab here, library, is using PerfSonar 5, which is the latest stable version of PerfSonar, right? So you'll be able to deploy an instance and do all these tests and basically understand all the configuration that you would do. Once you complete this lab library, you should be able to deploy your own PerfSonar node at your campus or at your organization's network. I will conclude with, so we still have 5 more minutes. What I'm gonna do in those is just demonstrate here one scenario where PerfSonar could be of help, right? So this is from DSNet websites, the one that also George talked about, and I placed it into the chat. So this is showing some real issues that happened in the network and how PerfSonar was able to troubleshoot those issues and fix the problem. So what we have here basically is we have a national lab on the left-hand side, and you have a campus, the right-hand side. And basically, we have PerfSonar nodes, we have data transfer nodes, but by sending data from the campus to the national lab, we saw that the performance is low. So we're trying to troubleshoot where's the problem. And if you see the path here, we have ESNet path around 30 millisecond, and then we have Internet 2 path around 15 millisecond. Then we have a regional network path, 2 milliseconds, and then you have the campus path here, which is around 1 millisecond. So if you are sending between these two devices, you're getting low performance. Where is the problem? It could be at any of those links here, or it could be internal in your network or in the collaborator's network. So how can we find the problem? Now, what we did here, we basically reproduced that experiment into Mininet using the labs that we created. So once you complete the labs, you'll be able to do something like this. So I'll just run this demo here. So we have the national lab on the left-hand side. We have the university campus on the right-hand side. We have DTNs. They are trying to send data to each other, right? And you can see here, we have a lot of PerfSonar nodes along the path. okay? So the first step we're gonna do is start a data transfer. We're gonna use iPerf here just to simulate a data transfer. As George was saying, it could be like basically through Globus, or Grid FTP, or any data transfer tool. So we are using here iPerf3 from the national lab to the university. We are expecting 5 gigabits per second, but the throughput was low. It was less than 200 megabits per second. So there's something wrong. We want to know what's happening. Now, keep in mind that you are here, right? As an engineer, you don't know all these devices here. So the first thing you need to do is try to discover the path. Now, we will use Persona for this. We assume that we have a Persona node in our national lab. So I'm going to schedule a task here, which is a round trip time task, by simply using ping, basically. And we specify the destination is the university's Persona. So schedule the test, wait for the results. It's telling us that the total RTT is around 49 milliseconds, which is basically adding the millisecond of each of those different networks that we discussed. Okay, next, what we will do is do a trace route test from the national lab all the way to the collaborators, which is the university. And now we will see that, well, these are the different devices that our packet traverse. So we have some routers from ESNet, we have routers from Internet 2, we have regional networks router, and then we have the border router on the university, and then the Persona node. Now, keep in mind, this is all emulated, so these are fake IPs. This is not real network, but I just replicated the scenario here so that we can visualize how it works. Okay, so now we know that we have these devices in the middle. We try to map them, right? So we have 4 routers. These are for ESNet. We have 2 routers for Internet 2, and then we have 2 routers for regional. So this is how it looks like for us. All right, so now we want to try to figure out why are we getting low performance. So I'm gonna schedule a test here, a throughput test. This is gonna be from the ESNet to the regional. One of the nice things about Persona is that it allows you to specify the source. So you don't always have to issue a test from your own local node. You can issue tests between any 2 global Persona nodes that are available, right? So here I'm saying I want to issue a test from ESNet, so from the border here, all the way to the regional network. So I want to see if the problem is in my network or it is in the external network in the WAN, right? And I'm trying to isolate here. So I'm running this test and then we wait for the results. By the way, the video here is edited. Typically, it takes a little bit of time to run the test and gather those results. So you can see that it's 10 gig. So now we can be sure that the path from the ESNet all the way to our regional networks, the collaborators regional network, is a clean path. We are getting 10 gig. So that's not the problem is not outside. Now we're gonna run another test also from ESNet, but now all the way to the university. So we wanna see if the problem is in that part there of the collaborators. Now running this test, we notice that the performance is low. So what would that tell us? We know now that the problem is in the university's network, in the collaborators, right? Because we made sure that the path is clean in the wide area network. It's not there. It should be on the destination. So why didn't we do a test from this regional network to the university network? We could have done that. But the problem is if you do that, the RTT is short. And then what will happen is that the TCP performance would be good because even if you have some packet losses because of something happening in the university, but because the distance of the regional network to the university is small, you end up having good performance. So instead, what we did here, we selected a longer path on purpose so that we can have similar behavior to how TCP works, basically in the original path. So now we know that the problem is in the university or our collaborator, right? So you talk with your collaborator, tell them, hey, there's a problem there, because we know that there's nothing wrong on our side. We check everything, the buffers, the configuration here. And we check that the path and the wide area network is clean, so there's nothing wrong there. There might be something wrong happening in your network. So then what they would do is they would go and try to inspect. One of the key problems could be buffering, right? We talked about that a lot in this workshop. So what I'm doing here is I went to one of the routers and just tried to see the counters, right? We also highlighted the importance of looking at counters. And then looking at the counters at the router, we saw that, well, this is the buffer size that we have, 250 kilobyte. It seems very small, right? And then we have some packets being dropped because of buffer overflow. So now we know what the problem is. Our buffer is not large enough. Now, this could be because the router is not, capable, but routers also have configurable buffer sizes. Some of them, not all of them. So you might have a high-end router, but it's not configured to use a large buffer size. So if that's the case, all you have to do is log into the router, increment the buffer size. So now we calculate the BDP, the bandwidth delay product, because we know it's 5 gig and 50 milliseconds. So we modify our router buffer size here to accommodate for that, which is 32 megabyte. And then after that, we can run our test again and see if this fixed the issue. All right, and as you can see now, the throughput went up to the expected value, the 5 gigabits per second. So this just shows one problem that we were able to detect through Personar. But imagine if you don't have Personar, and that problem could be in any of those links. And as I said, you cannot just do like direct testing between these two links or between two links that have short path, because TCP will not behave the same as if it would behave in a large wide area network. But with Personar, you're able to schedule those tasks even if they are not your Personar node. So as a national lab here, we were able to schedule a test from ESNet to a regional network, right? We got the results and then we use those to try to localize where the problem is. Okay, so this is just a short demo. Again, once you do the lab, you should be able to work through this and then construct your own scenario. All right, well, that's it for this first day of the workshop. Thank you all for attending. If there are any questions, please feel free to leave them in the chat. And one thing I want to ask you is to fill the survey. So there's a link at the bottom of day one of this workshop. It's just a short survey. Please, we would really appreciate the feedback that you would give us so that we can improve for future workshops. Now, if you are planning to attend day number 2, it will be also a workshop that has hands-on sessions. The topic is a little bit different. So here we are talking about per packet processing with high performance, something like P4-DPDK, very high-end new technologies for accelerating packet processing. So I would invite you all to attend day number 2, which is this Thursday, in the same time as the first day. One final thing, the video for today is gonna be uploaded to the website, so you should be able to see it in the agenda of day 1. So with that, I will conclude. Okay, we have a question. So can you remind us how long we'll have access to that? So by default, the policy is to have it for 6 months. However, if you need more, just shoot us an email and we can extend it for more if you want. All right. Is there any other question? All right, thank you all again. Thank you, George. Thank you, Jose and Ali, and Jennifer. So we will see you on Thursday.